So live streaming has started?
Yeah. Yes.
You can see my...
Yes. Yeah.
Yes.
Okay. I'll unshare it. How do you unshare it? You can like cut me out, I think. How do you unshare?
On the top of the
red button must be there on the top.
There is a stop share, Justin.
Oh yeah, right. Yeah.
Camelia, can you share the screen now? Are you able to share the screen?
yes. 1 second.
We can start the recording now, right?
Yes.
Okay, I'm starting the recording.
You can start the recording. We'll wait for a couple of more minutes. A lot of people are joining.
पूरी अच्छी
Shall we start?
Yeah, we can start. You're already 2 minutes.
Yeah, I think let's
Yeah.
start.
Yes. So Camelia, you can start.
Yeah.
Okay. Hello, everyone. This is Camelia, and on behalf of Center for High Energy Physics, IISc, I welcome you all. We meet here today to discuss Theoretical Perspectives, a decade after Higgs boson discovery, organized by CHEP. So, as you all know, it has been 10 years since the historical discovery of Higgs boson, but the quest to understanding fundamental physics, however, did not end there. In fact, there are many questions. There are always many questions. For example, is the discovered Higgs boson really the standard model Higgs? Is the Higgs composite in nature? Can Higgs be a portal to the elusive dark matter and other new physics particles? And how does Higgs boson come into the picture in relation with neutrino physics and other beyond standard models, for example, supersymmetry? So, and of course, can Higgs explain the inflation of the early universe? And many more such questions. We gather here to learn about the progress we have made so far from a theoretical point of view. But of course, that is not all that needs to be discussed. As ILLITSI begins their run 3, we look forward to collecting more and more data and have more precise measurements. So this is a really exciting time for particle physics. But sadly, we are constrained by the short duration of this meet, which is just for one day. So we will not be able to cover those interesting and very important experimental aspects. We hope to conduct a similar discussion on the experimental side of it too. That is the current status and the development of future colliders. But right now, without further ado, let's dive right into it. And throughout the meet, there will be certain rules that the participants are requested to follow. So I'm just reading them out. So we request all to follow these rules. Please mute your microphone while listening to the talks. If you have questions in the middle of the talk, drop your questions in the chat box. Okay, the coordinators will pass the questions to the speaker in due time. After the talk is finished, you can raise your hand and ask questions at your turn. Unmute yourself only while asking question. Please check that you have again muted yourself after asking the questions, and you may turn off your camera to save the bandwidth. And all the talks will be recorded and live streamed on YouTube. And so now, and also the talks that are of 45 minutes. So I will be alerting the speaker after 35 minutes, and the talk will be for 40 minutes, and you'll have 5 minutes for taking questions. So without any more delay, we will begin the session, and we shall begin the session with a welcome address by the chair of CGP, Professor Justin David. So I welcome him to share a few words, and I'm now stopping my screen share.
Yeah. Hi, everyone. I'm Justin. Let me just share the screen to begin with. So, yeah, it's the screen. So I'm happy this opportunity has been given to me for beginning this exciting conference. So let me just take the time I have to introduce the Center for High Energy Physics, which is in IISc. We're a sort of small center compared to the other departments in IISc, but we have an interesting history and we have an interesting contribution. So the center came in existence around 2004 in the present form, after reorganizing the Center for Theoretical Studies, which was conducting similar research programs. We conduct various programs in the areas of high energy physics, quantum field theory, and quantum gravity. I will just give you a brief introduction to some of the things we do by just sharing the people who do it and what they do. So the major research areas are, we have areas right from formal quantum field theory to low dimensional condensed matter systems. And in the areas you are interested in, we do various standard model searches, standard model physics beyond the standard model. A lot of emphasis of our research is actually of the people's research here is actually on precision measurements in the standard model and prediction of certain particles and of certain phenomena. We have also recently added astroparticle physics to this thing, because that's sort of the frontier we expect to be. And in QCD, we have also expertise in QCD. Again, it's on precision data in QCD, the phase transition, temperatures, and so on. And we also have a little formal group in gravity duality, string theory, and quantum gravity, and some expertise in quantum information too. So this is sort of the rough area. You get a picture by just seeing the topics I'm listing. And let me just introduce some of the people and the research. We have 13 faculty members and an honorary professor, of course, in is there in the audience. So here I group them into sort of areas. I mean, I have organized them in a particular way so that you get a perspective. So the theoretical particle physics, in which I think most of the people here are running this meeting. There's Anand. He does chiral perturbation theory, Grant unification, supersymmetry. He's also involved in precision standard model, determination of precision parameters in the standard model. I mean, G-2, I think he's been involved in pion physics. Biplab, he does, this collider phenomenology, supersymmetry, and Higgs phenomenology. And he has some recent work on the Higgs phenomenology. And Rohini, everybody knows Rohini. And she also does collider physics, Higgs phenomenology, supersymmetry. Ranjan does astroparticle physics, various predictions in astroparticle physics, and Sudhir also does supersymmetry, grand unified theories, and physics beyond standard model. Right now I think he's into dark matter too. So this is people I sort of put together who work with large collaborations. So there's Jyotsna, who works with the CERN collaboration, CMS collaboration at CERN. So she's also been recently, I think, been involved in determining Higgs trilinear coupling. I think that group, the CMS group, and Prasad works in the lattice gauge theory, and he does QCD at finite temperature. Basically, thermodynamic properties of QCD, finite integral potential. And these are people who work in applications of quantum field theory to other systems. As Apurva, he used to work in lattice, but now he does mostly quantum computation and quantum information. Diptiman does low-dimensional condensed matter system. And Sachin works in, actually, right now he has effective models of QCD. He studies effective models of QCD, models QCD by a matrix model, studies its parameters, studies the mass spectrum, actually. And then there's this formal string theory and quantum gravity group, including me. There's a recent addition we have, Gaurav Narayan, who works on quantum gravity. There's Chetan, string theory in black holes, and India, who works in S-matrix mostly now. So this is us, and I guess you get a perspective of what we do by this. But this, the most importantly, actually, one of the jobs is teaching and mentorship. We have 8 postdoctoral fellows, 39 PhD students, and 11 students, roughly 11 students every year who do a project with us. And we teach courses in the IISc undergraduate program, the integrated PhD program, and the regular PhD program, and advise UD students. Of course, we help the postdocs too. These are mentorship duties. And the other activities, we run an active visitors program. Presently, we have Professor Sopan Chattopadhyay, who's a particle and accelerator physics He's a visiting professor with us. And then we host, of course, undergraduate program students across the country. And just as you're part of it now, we conduct national level schools and workshops. This is one of them. So the organizers have planned to have 3 online meetings, perspectives of a decade after Higgs boson discovery. And you are presently attending the theoretical perspective. Eventually, they plan to have the experimental perspective and future perspectives, and all this will be held before the year ends. And hopefully, the conference, I'm sure, it'll be exciting and productive for all of you. Welcome to the meeting here.
Thank you, Professor David, for your kind and informative words. Our first talk will be presented by Professor Rohini Godbole, and I again remind you the rules for the duration of the talk. So the talk will be of 45 minutes, which includes 40 minutes of talk and 5 minutes of taking questions. I will alert the speaker after 35 minutes. Welcome, Professor Godbole.
Okay, thank you, Camilla. Camellia, rather. I'm sorry, too early in the morning. Okay, so it's really nice, a very informal discussion that we had of. I mean, when I suggested this, I had a thought of maybe a 2.5 hour meet to celebrate the 10th anniversary, and thanks to Anand, Ranjan, and Sudhir, and Biplab, this has changed into a much more serious affair. So thanks very much to all of them for beginning to organize this. And I am going to be talking about the history. So let me begin by sharing my screen. Yeah, I hope everybody can see my screen.
Yes.
Yeah, good. So I just want to tell the early story about the Higgs boson. So my plan is that I will really begin at the beginning, and that I call massive W. Then the second part of the beginning is the spontaneous symmetry breaking. And then combination of the 1 and 2 is the famous model of leptons suggested by Steven Weinberg, which is the birth of the Higgs as we know it. And in fact, Benjamin Lee used to call it Weinberg's particle till Weinberg suggested that it be called the Higgs. So then I will go to the Higgs properties and what we knew when the Higgs was postulated, what we didn't. And then very briefly I will tell about the theoretical bounds on the Higgs mass and the indirect bounds on the Higgs mass. Putting these two together, I will present to you the landscape on the eve of the discovery of the Higgs, that is 10 years ago. And as I go along, I might just weave in some of my own early involvement in the story. So the first one is I begin by a dedication to my PhD supervisor Jack Smith, whose supervisor for his master's thesis was Peter Higgs. So this was my own earliest connection with Higgs. And this is Jack Smith with Peter Higgs in the Nobel Prize ceremony. As you can see the date, this is in 2013 in Stockholm. I personally began my graduate studies in 1974, and this was the year when JPSI was discovered. And one of the most significant, why it is called November Revolution, is that this was really the first solid indication that the gauge field theoretic description of weak interactions that was suggested by Glashow, Weinberg, and Salam theory based on the minimal gauge group SU2L cross U1 was indeed a reality. And if that is the case, then the Higgs boson as a real entity began to be taken very seriously. And that is also the time when the famous nanopolars Ellis Gaia paper about giving the sort of picture of Higgs boson in the Nuclear Physics B came out. So I also would like to say that when we are celebrating 10 years of the Higgs discovery, we are celebrating more than half a century of the Higgs itself. So let us begin at the beginning, that for weak interactions, the beginning was the V minus A theory, which was put forward by Sudarshan Marshak and Feynman-Gell-Mann separately. And as Weinberg puts it, V minus A was the basis, it was the key, as he calls it. V minus A was the key. So if all of us remember that the beta decay interaction describing the nuclear beta decay around 1957, this was the Sudarshan Marshak theory, which said that this can be effective, this will be described by an effective Hamiltonian, which is given as a current interaction, product of the hadronic current with the leptonic current. And the difference between the leptonic current and the hadronic current was really that in the case of leptonic current, this was just 1 minus gamma 5. The electron was always left-handed, whereas here it was 1 minus mod Ca over Cv gamma 5, where this was a mod Ca over Cv was just a number slightly bigger than 1. So this was the Sudarshan-Marshak V minus A theory. So in fact, basically not just the beta decay, but actually all the weak interactions that were observed till then could in principle be written in terms of the product of two currents, and the currents are either vector or axial vector. So just the combination of vector and axial vector current meant that you could in fact think about these point-like 4 fermion interaction as being caused by an exchange of a spin 1 particle. So this actually is the beginning of thinking that the weak interactions might be thought about as being caused by the exchange of a massive spin 1 particle, and that's the name, the weak boson. Actually the name weak boson was given by Schwinger before even the V minus A theory was put forward. And in fact, Sudarshan and Marshak mention that the V minus A nature of the interaction actually lends a lot of support to the idea of the weak boson, charged boson that was postulated by Schwinger in analogy with the photon that was already known. So this was the extension of the known QED, which was, I'm anticipating already gauge theory here, and this is the photon vertex in the gauge theory. And corresponding to that, Schwinger actually had postulated this W boson exchange causing the weak interactions, and of course because it is supposed to be very heavy, this all came in already in Schwinger's time, and therefore what it manifests itself at low energy is a point interaction, and it is this point interaction that was indeed found by Sudarshan and Marshak and Feynman and Gell-Mann to describe the entire set of gamut of weak processes that was seen at that time in 1957. So this is where the W boson sort of took its life. But then one started calculating the cross sections in the V minus A theory, thinking of this as a current-current interaction, and then the total neutrino electron cross sections, Gedanken experiment, one finds that this cross section will actually grow with energy, and there is this linear rise with energy of the total cross section. So clearly cross sections cannot keep on rising with energy infinitely like this. At some energy this will actually violate unitarity, and you can do a partial wave decomposition and see that the unitarity is violated when the total center of mass energy, square of the center of mass energy, is bigger than this number, and this is really the Fermi coupling constant or the muon decay coupling constant. Now indeed, once you put in a massive W, then the unitarity will actually be preserved because there will be a factor involving mw square in the denominator, and therefore mw should actually be less than the energy at which unitarity is going to be violated. So therefore the first bound on the mass of the W comes from this expression, which says that the W mass is not infinite, it is finite, and it is less than or equal to 300 GeV. So the idea was fine, Schwinger's W boson should be massive, but there should be a limit on this mass already by the considerations of the unitarity. But this actually raised other problem, that if you now calculate nu bar going to W plus W minus, and then you find that those amplitudes start violating unitarity at somewhat higher energies, and that happens because of the longitudinal degrees of freedom of the W. So in fact, Glashow was the first one to notice that if we think of a gauge theory based on SU2 cross U1 gauge group, we can actually tame the high energy behavior of these amplitudes. So this is a different story. This was a total cross section. This is the 3-level amplitude of nu bar going to W plus W minus. And now once the W boson have masses, you can if there is a problem, and that problem will be cured if you have extend the particle spectrum of the theory based on the SU2 cross U1 gauge group. So now, however, while this is right that the gauge theory will remove the problem of unitarity violation in nu bar going to W plus W minus, the massive W's cause another problem. And that was, this is a case of a tarpaulin actually, and this is where the Higgs actually come into the picture. So QED as a gauge theory by this in already 1960s was very well understood, established, and Young and Mills had already put forward the non-abelian gauge theory idea. And then one said that the gauge group, SU12 cross U1 gauge group, was a very nice gauge group as pointed out by Glashow. This was a 1961 paper. the gauge theory of weak interactions will not be possible because the massive gauge bosons mean that we cannot have this Lagrangian to satisfy the any gauge symmetry. And at this point, nobody knew how to sort out this problem. And in fact, not many other than the inventors of the standard model were thinking very much about weak interactions as gauge theories at this point, apart from people like Glashow. At the same time, in the theory of strong interactions, there was basically a development in understanding of symmetries. And what people had seen that there were many symmetries which were approximate symmetries, like isospin, the Flavor SU3. Then in fact, for pure leptonic weak currents, as I already pointed out, CV over CA was 1, and for beta decay, CA over CV was different than 1. And this very difference from 1 for strong interactions was considered that this is happening because of the effects of strong interaction on the axial vector current, that the vector current remains unaffected by strong interactions, similar to the fact that the proton charge and the electron charge are one and the same. There is no renormalization due to strong interactions of the vector charge, and the axial vector charge is only partially conserved, so it receives small corrections. And this was understood as happening due to breaking of chiral symmetry. So therefore people generally started talking about how broken symmetries can be described. In that time, Goldberger and Treman had proved that the CA over CV, which was 1.25, this variation, the deviation of CA from 1 was actually understood by saying that the divergence of the axial vector current was proportional to the pion field. So this was all happening in strong interaction context. But then how do you understand this spontaneous breaking of the symmetry? This was the idea that had been floating around at that time. And in fact, the spontaneous symmetry breaking, which you and me know as the cornerstone of the weak interaction SU12 cross U1 model, was actually first introduced in the context of strong interactions. And in fact, Weinberg, Salam and Goldstone, they proved a path-breaking theorem in 1962. And I'm just producing lines from the abstract. Some proofs are presented of Goldstone's conjecture that if there is a continuous symmetry transformation under which the Lagrangian is invariant, then either the vacuum is also invariant under the transformation, or there must exist spinless particles of zero mass. Most of us studied this in the beginning of our study of standard model. And since at that time no spinless massless particles were known to exist, this seemed to be the end of the use of spontaneous symmetry breaking in field theory. But then came the genius of Nambu, and he actually made the whole sense by pointing out that the Goldberg-Treman relationship, which was put forward and understood in terms of the breaking of the chiral symmetry, he said that actually this could be completely understood if the chiral symmetry of the strong interaction is spontaneously broken. If the symmetry was an exact symmetry, pion would have been massless in accordance with the Weinberg, Salam and Goldstone theorem. But since the chiral symmetry is not actually exact, we have an almost massless pion, that was the pseudo-Goldstone boson. So fine, at this point, spontaneous symmetry breaking was being applied only to the theory of strong interactions, and approximate symmetry of chiral symmetry was being broken spontaneously, and there was the pion as the pseudo-Goldstone boson. Now this spontaneously broken symmetry was visible in the interactions of the Goldstone boson, in this case the pion. Now around the same time, in another year, Anderson showed that in the non-relativistic context, including Yang-Mills interaction, the problem with zero mass Goldstone excitations vanishes. So now there are two possibilities. One was that if it was approximate, then you would have a pseudo-Goldstone boson, so not exactly the massless excitation. But here Anderson gave a completely different perspective into spontaneous symmetry breaking, saying that that is the abstract from his paper. It is also shown that Schwinger's criterion that the vector field mass not equal to 0 implies that the matter spectrum before including the Yang-Mills interaction contains m equal to 0, but the example of superconductivity illustrates that the physical state spectrum does not. So this some comments on the relationship between these ideas and the zero mass difficulty in theories with broken symmetries are given. So Anderson was already seized of the fact that spontaneous symmetry breaking can be used such that the problem of the zero mass Goldstone will not exist if we make the symmetry to be local instead of the symmetry being global as it was being thought in the context, for example, of chiral symmetry. And then there were two different theoretical issues. I have tried to give you one which said that the local gauge invariance required massless gauge bosons. The properties of the weak interactions indicated we must have massive gauge bosons. Now, how to have massive gauge bosons and still have a Lagrangian that respects gauge symmetry, and that, as I said, with the Goldstone theorem, Weinberg, Salam and Goldstone theorem, one had said that the spontaneous breaking of a continuous symmetry will always lead to a massless scalar, and this combination of SSB with a local gauge theory, we combine this with a local gauge theory and we get a healthy way of getting massive gauge bosons, still respecting the gauge invariance, and this was the same observation by Anderson. And indeed, this is what the standard thing which you read and study in the first lecture of perhaps the standard model, that indeed we can start with a Lagrangian which contains complex doublet scalar, then which contains the wrong sign for the mass term for the scalar, then there is this self-coupling, and then there is this local gauge symmetry. Now, the physical vacuum will indeed correspond to the non-zero vacuum expectation value of the scalar complex scalar field Y by V over root 2, where V is related to the parameters of the potential in this manner. And then indeed, now if you expand around this minimum, then one finds that one gets the theory of a massive gauge boson. Here there was no mass term for the gauge boson, but a mass term is generated and the mass is given by G times V, where G is involved here in F mu nu, and a physical scalar eta which is with the mass root 2 times mu. So this was indeed the basic Higgs mechanism. Now in this example, we started with a complex scalar and one massless gauge boson, and after spontaneous symmetry breaking, one ended up with precisely one massive gauge boson and one massive scalar. So in general, the number of scalars will depend on the pattern of symmetry breaking. So we do have one massless gauge boson in nature. So if we want to apply it to real life, something slightly more complex has to be done. Actually, I should also point out at this point that neither of the proponents of the spontaneous symmetry breaking mechanisms, there were 3 or 4 of them, knew about the issue with electroweak interactions. They were looking at SSB from the point of view of applying it to strong interaction. So actually, they did not apply this solution to the problem that actually existed. Higgs actually mentions this specifically in an interview. Whereas Salam and Weinberg were looking at SSB, at the same time they were also looking at phenomenology of the weak interaction, and they then imagined that this gives an absolutely wonderful way of generating the non-zero mass for the W boson, but that means that there will be a non-trivial scalar degree of freedom, and that's the Higgs. So this is the famous paper of model of leptons from 1967, and I would actually like to read the first few lines to you. Leptons interacts only with photons and with the intermediate bosons, these are the Schwinger's bosons, that presumably mediate weak interactions. Mind you, presumably, what could be more natural than to unite these spin 1 bosons into a multiplet of gauge fields? Standing in the way of this synthesis are the obvious differences in the masses of the photon and the intermediate meson and in their couplings. We might hope to understand these differences by imagining that the symmetry relating the weak and electromagnetic interactions are exact symmetries of the Lagrangian but are broken by the vacuum. That means they are spontaneously broken, and he just speculates here the model may be renormalizable because the Lagrangian is gauge invariant, and it was this sort of idea that they put forward, and this is actually the Lagrangian that he wrote for the in the model of leptons paper. And indeed we have this picture, standard picture, that there will be 3 SU2 gauge bosons which are massless before the spontaneous symmetry breaking. There is a U1 gauge boson. They mixing them, they would produce the Z0 and the photon and the charge current W plus and W minus, which were the ones which were initially envisaged by our friend Schwinger. So Glashow's paper actually had electroweak unification, but he didn't have a model for the non-zero masses of the weak bosons. Therefore, there was no prediction for the relations between MW and MZ, and clearly there was no prediction of the Higgs boson. So in that sense, this paper really differed, because these papers not only gave a precise relationship between the W and the Z masses, but also said that there will be a scalar field which will be left over after spontaneous symmetry breaking, and therefore the difference between the Glashow paper and the Salam-Weinberg paper was really the additional scalar, the Higgs boson, because they had used the Higgs mechanism to give masses to the W and the Z in the gauge invariant manner. So in that sense, Glashow was on one hand, and Weinberg and Salam were a step further. Actually, Weinberg went even one step further, which even Salam didn't take, and that was that Weinberg actually also used the same mechanism to give masses to the leptons. So Weinberg, Salam, as I said, they used the Higgs mechanism to make the gauge bosons massive. But remember that this was only one way of achieving it. It was likely, not necessarily probable, that Weinberg's model was right, and still there is no elementary Higgs. So the 1967 paper, as I said, has discussed all this. And one of the things one should remember, which will be pertinent for our further discussion, is that the choice of representation to which the scalar phi belonged, it actually decides the couplings of the Higgs bosons with the fermions and the gauge bosons. So even if you granted that it was elementary, what else did we know? This choice of doublet was ad hoc. That is first point that I want to make. Secondly, nothing was known a priori about its mass, and only thing that was very nice was that couplings to all the gauge bosons and fermions were known thanks to the mass generation mechanism, that is thanks to Weinberg essentially. Alright, so here was the story that in the paper phi was chosen arbitrarily to be a complex SU2L doublet, and you had this 8 degrees of freedom with 4 massless gauge bosons, 4 scalar degrees of freedom in the scalar potential, and when you do the SSB and look in the unitary gauge, you are left with 3 massive gauge bosons, 1 massless gauge boson which was the photon, which will of course have 11 degrees of freedom, and there will be 1 physical scalar which is the 12th degree of freedom. So clearly we didn't create any new degree of freedom, but they simply get described in different forms. Now here the first thing that I want you to emphasize here is that the ratio of MW to MZ depended on 2 parameters. One was the mixing angle, mixing between the B and the W3, and the representation to which the scalar phi depended. So therefore, for the choice of the doublet in Weinberg-Salam model, in Weinberg's paper in fact, rho is equal to MW square over MZ square cos square theta W, which is 1. So what is this rho? This rho also had an alternative interpretation and understanding as the ratio of the charge current interactions to neutral current interactions in the effective current Lagrangians, and therefore there is a independent theoretical experimental way to measure rho, and then one can compare and contrast with this once you measure cos theta W and see whether this doublet story actually carries weight. So the Weinberg's model had suggested one very robust prediction, which I have put here as in bold: existence of the Z boson, the weak neutral currents, and with the relative strength of the charge and neutral current interactions be given by rho, which is then predicted to be 1 for the choice of the doublet. In addition to that, there are existence of the additional scalar, 1 single scalar, but since the choice of the doublet is ad hoc, the prediction that there will exist 1 scalar, additional scalar, and rho will be 1, both these are less robust predictions. Alright, so this is the standard model Lagrangian, which was the proof, now we sort of make a big jump from 1967-74 to something close to 1985, when the Large Hadron Collider was being planned, imagined and designed. And there you see that the Lagrangian was the proven gauge sector. By this time you had actually proved that the electroweak theory is a gauge theory. Then interactions between fermions and the gauge bosons are described by this covariant derivative. The masses seem to be generated by interactions of these fermions with the scalar, but this part was not established at that point, and the red part, the scalars, were not at all seen, and this is somewhere around 1980 that we can talk about. Now another 10 years passed. Before those 10 years passed, let me just now summarize the predictions of the Weinberg, which are present in Weinberg paper, and there you see that the masses of the W and the Z are related to the couplings of the SU12 and U1 gauge group G1 and G2 and the vacuum expectation value V. V can be determined experimentally in terms of the muon decay constant G mu, and you don't need to know mu square and lambda separately, but you know V in terms of V, which is determined V in terms of G mu itself. Now you can go ahead and say that all the masses are related to G1 and V and G2 and V. And then the Lagrangian for the scalar sector also involves the lambda, okay, but lambda is related to mh square and V. So now we have, please note here, connection between lambda and mh. So at this point all we knew was G1, G2 and V. Further, one knew that Higgs is a spin 0 CP even object, and the couplings of the Higgs with the fermions, couplings of the Higgs with the gauge bosons, and the self coupling of the Higgs as well as the coupling of the Higgs with a pair of gauge bosons, all these are actually given in terms of the Weinberg-Salam model, and the couplings to GG and pair of photons are loop induced, and those loop induced couplings were also pretty well known, but they depend, now begin with this, they depend on the additional particle content of the model. These are not determined simply by the symmetry breaking and principle and the gauge group. So here I sort of summarize the loop induced couplings, that in the standard model the contribution is due to W and top loops for the H gamma gamma vertex, and for the Higgs gluon vertex it is the top contribution. New particles beyond the standard model will contribute in the loops, and those contributions are actually non-decoupling for chiral fermions, and that's a very important point, because if a fermion gets the mass from the Higgs mechanism, then it will have couplings proportional to the mass of the fermion with the Higgs, and then they will enter the loop, and hence indirectly by looking at the Higgs to gamma gamma and the Higgs to glue couplings, you would be able to probe if there are any more chiral fermions than are known. So that was the idea. For a Higgs mass of 125 GeV, which is the Higgs mass at which it was discovered 10 years ago, the photon width of the Higgs is actually proportional to the loop amplitude which is caused by the W and the loop amplitude caused by the top exchange, and in fact it is dominated by the W contribution. In fact, AW is about -7 and A top with the mass of the top quark 175 GeV is about order 1. So it's really a small quantity compared to the 7. In the very early days, the top quark had not yet been discovered and it was considered to be light. So in that time, for the heavier gauge bosons, in fact Higgs boson, the dominant production mode was not GGH but was the W fusion, because anyway if the top is not heavy, then in the glue fusion, of course if I calculate the same thing for the glue fusion, W cannot contribute because glue do not carry weak charge, and then the top is not very heavy. So in which case the glue fusion production cross sections were considered to be rather small for the large Higgs masses, and therefore earliest vision when I was a graduate student, we thought that the dominant mechanism for production of the heavier gauge Higgs boson would actually be the W fusion. So as I said, when did people start taking Higgs seriously? This was the weak neutral current discovery in 74 as well as the discovery of JPSI, which made people realize that yes, SU12 cross U1 seems to be correct, and exactly by the same time the renormalizability of the spontaneously broken gauge theories was proved by 't Hooft and Weltman in 1977. So it was all coming together and people started believing that the gauge theoretic description of weak and spontaneous weak interactions with spontaneous symmetry breaking seems to be the right thing. And then came this paper in 1976, which was this profile of the Higgs boson, Allis, Gaia and Nanopoulos, which I referred to in my early talk. And the situation, I quote from that paper, situation with regard to Higgs boson is unsatisfactory. So what they are saying here earlier is that by 1976, the gauge theoretic description of weak interactions seemed to be pretty good. Everything was described in terms of sin theta w and g1 and g2, and you could actually describe all the neutral current interactions, everything in terms of the standard model. But where was the Higgs boson? So it said that this may well not exist. The symmetry may not be broken spontaneously, may be broken dynamically. Therefore, confirmation or exclusion of the existence of the Higgs boson would be an important constraint on the gauge theory model building, and they said that at least right now, no way is known to calculate the mass of the Higgs boson in the context of the Weinberg-Salam model. So what did we know about its mass? So you go back and remember, it depended on lambda and mu square. Now, or v. Now, these are parameters of a Lagrangian, and we have no idea if they are not related to any other observable. How are we going to be able to predict MH? Are there any theoretical considerations? And that's where this seminal paper, which by Benjamin Lee and Thacker and Quigg, that came in, where they did is that, you remember I talked about nu bar going to W plus W minus, which was actually discussed by Glashow in a paper. Now this is actually continuation of that idea, and people looked at the amplitudes E plus E minus going to W plus W minus, and indeed what Glashow's work had shown is that nu bar going to W plus W minus, this has a bad high energy behavior. It gets cured by the Z exchange with the ZWW plus coupling exactly as predicted in the standard model in the SU2L cross U1 model. But if I consider, instead of nu, I consider the electron, the sum of these two amplitudes still had a residual bad high energy behavior, which grew with the energy as the logarithm. And indeed, the exchange of the Higgs boson X channel spin zero exchange actually tames that bad high energy behavior of this amplitude. And once you add all the three amplitudes together, three diagrams together, give rise to a W plus W minus, E plus E minus going to W plus W minus, which is not rising with energy in fact, but which has a very good high energy behavior. In fact, the Thacker paper, Lee Thacker and the Quigg paper calculated all kinds of amplitudes in the standard model, and they showed that each of these scattering amplitudes at the tree level had bad high energy behavior, but they cancel each other, the bad high energy behaviors, only for the cases where the coupling of the Higgs boson and the coupling of the Z boson with the W's is exactly as in the standard model. Further, if I had heavy fermions and if I looked at TT bar going to W plus W minus, for example, then one would need the HTT coupling to be exactly the same as in the SM, which I talked here about with the E plus E minus also. So this was actually the discussion already of this paper that I have been discussing again and again. And this first time in this paper, Lee, Quigg and Thacker therefore predicted that there should be an upper limit on the Higgs mass of about 780 GeV. Another way of understanding the same thing is that, remember the relationship between MH, lambda and V, that if the MH is too large, then the self-coupling lambda is very large, and that means that it will be a strong coupling theory. So if you want to have a light Higgs, that is traditionally we said that it would be the weak coupling theory, and otherwise if the Higgs mass is too large, the Higgs might be strongly interacting because lambda is actually rather large. So actually there is a very interesting statement that I would like to make, is that Satish Jogrekar, who was a graduate student of Benjamin Lee, and also Tiktopoulos, Cornwall, I think a whole lot of other people, had actually proved that you could actually derive the particle content of one generation of the standard model, including the Higgs boson, by simply demanding the W plus W good behavior of the W plus W minus scattering amplitudes. So these is the upper limit on the Higgs boson mass. Then are there any other limits? These are pure theoretical limits, right? Now the second set of theoretical limits came from triviality and stability bounds by demanding that the quartic coupling in the Higgs potential, as I said, this is something that existed in the original Weinberg paper, so we are not putting any extra assumptions, So if you look at this potential and you demand that the quartic coupling that is involved in this potential remains perturbative under its evolution under loop corrections, then where do the loop corrections come from? This is the self-coupling, lambda h4. Now you start calculating the loops and then ask the question, how do loops change lambda? So if you look at how loops change lambda, then by demanding that this lambda, there are two conditions. One is to say that lambda, just see the form of the lambda under the loop corrections. You can calculate the renormalization loop equation for your coupling lambda, and then lambda q square is lambda v square divided by this factor. And here what I have done is that I have said that it's lambda is becoming large, so all the other couplings are actually neglected and only corrections are coming from the Higgs scalar exchange itself. And now if you look at this form and ask the question that at some very high scale lambda is going to become very small, and at the end of it, it will actually become, so there are two ways in which you want to look at it. One is there are two kinds of limits that you are going to get, and here when you say that since there is this lambda has this energy dependence and it is going to blow up at some scale, the only way you can solve the problem is by saying that lambda was 0 to begin with, and that is then the theory would become trivial. So this is the upper bound on your mass of the Higgs at the electroweak scale by demanding that the Landau pole at which this will blow up to infinity lies below a certain energy scale. So this is the point that I already mentioned before, which I have written here, that we say that if we demand that the lambda should remain always in the perturbative regime, then we have to actually we go only to the final conclusion that lambda will be 0, and we don't want that. So that's an alternative view we take, which I already mentioned, that demand that the scale at which this lambda blows up actually lies below above below a capital scale lambda, and then the lambda, the scale at which the pole will exist is something related to V through an exponential, and if I put lambda c equal to lambda equal to 10 to the 16 GeV, you will find that mh should be less than 200 GeV, and this is the triviality bound by saying that lambda q square actually develops a pole below 10 to the 16 GeV would mean that the Higgs mass at the low scale, which is this lambda v square, should be less than 200 GeV. So now this meant that if you ever find the Higgs, the mass of the Higgs will tell you immediately what is the scale of new physics beyond standard model. The other point was when mh is small and lambda not large, the fermion and the gauge boson couplings will actually contribute to the evolution of lambda, and in fact as time went along, one started realizing that the top quark was heavier and heavier, and by the time of 1990s you already knew that the top was 175 GeV. So you could actually calculate this and then now demand that get a lower limit on the Higgs mass. Now by demanding, yes madam,
You have 5 minutes.
very good, I am more or less coming to the end of the story.
Okay.
So therefore you now demand that demand that the Higgs mass be such that lambda should not become negative, because lambda becoming negative is not something acceptable. Vacuum will become unstable, and indeed you can actually do this and get yourself a lower limit on the Higgs mass. And the earliest calculations of such stability bounds were actually done by Weinberg, and this was a paper in 1976 by Weinberg, where he said that the stability of the vacuum sets a lower bound on the Higgs boson mass, and at that time, since top quark was not known and he used only the W contributions, the limit on the Higgs boson mass was something like 3.72 GeV. And then he said in this case, the best place to produce the Higgs boson will be in the neutrino reactions. And in 1977, this is my own first paper involving the Higgs boson, where we had calculated the W boson fusion of the Higgs boson in neutrino proton reactions. Now, as we know, the actual Higgs boson in the W fusion channel in PP and LHC has become a very big deal. So this is actually the early story about the limits on the Higgs boson mass. So these are the limits which are coming from triviality. These are the limits coming from the vacuum stability. And the Tevatron had looked actively for this. And this is 2009. And one said that now, depending on where the Higgs boson is found, we will say that what is the scale of the new physics. That was the situation. And the task for the LHC was to find a Higgs in this very vast mass range from 70 to 1000 GeV. And as I said, with the mass of the top, which was known at that time, initially a lot of attention was focused on the VBF, and that is where some of the younger people will know about boosted jets in a big way. And this idea was suggested by Butterworth and collaborators to reduce the QCD background for the heavy Higgs searches. And many of us actually had been working on the vector boson fusion at that time, that because we thought that that might be the major channel for what is called the so-called intermediate Higgs mass. So, between 1986 and 2007, a lot of water flew under the bridge, and now we know much more about the Higgs mass using E plus E minus precision measurements. And I am going to skip this part, which is again a very interesting story, but since I don't have any time, I'm skipping the part how precision measurements at LEP actually give us the constraint on the Higgs mass. But I will now come here in 2011, where the searches for the Higgs boson at LEP had ruled out the Higgs masses up to 114, and Tevatron searches had ruled out the masses between 160 and 180. And this blue region was the region that was suggested for the Higgs boson from the radiative corrections that the Higgs boson mass can give to the precision measured couplings in the standard model. And the LEP had measured these precision couplings to a great degree of accuracy. These are the 4 slides that I have skipped. And this was the situation in 2011, that one said that the Higgs boson mass, the central value prediction was here 100 GeV, but at 2 sigma level you expected the Higgs mass to be less than something like 220 GeV. By the time you came on the eve of the Higgs boson discovery, that is 2013, this is actually 2012 June, at which point what had happened was this remains the same, the blue that I have drawn here, but you have whole lot of more and more experimental exclusions from LEP, from Tevatron, add to that the LHC exclusion. And in December 2011, frankly, the only point slither, that white slither that was left in the standard model was this white slither. So now how does it look on this famous plot of pure theoretical bounds? Because these are all experimental searches. At this point, these are experimental bounds. This blue is combination of experimental and theoretical considerations of the perturbative corrections, and these are pure theoretical bounds, vacuum stability as well as triviality. And then you see this was this thin slither. And now on the eve in 2012 January, we found that the Higgs mass range was restricted to this very narrow range with theoretical constraints, pure theoretical constraints, as well as experimental and theoretical constraints. And if the Higgs had not been discovered in 2012, where it has been, perhaps things would have been more fun, but in fact they would have been much more complicated, because if standard model was correct and its correctness was being proved to a great degree of accuracy by these studies of MW and MT, we would really have been in a pickle. And indeed, LHC, to everybody's relief, found the Higgs really in that narrow slither, and it gave us the final confirmation of the correctness of the model of leptons of Weinberg. Now where do we go onwards? Testing the Higgs self-coupling and using the Higgs to probe the BSM through the Higgs portal. That's where we are going to go. And I end with my own third slide on personal connections, that the way the data were reported on July 4th, 2012, in fact, what we had found is that this was the ratio of the observed rates with respect to the expectations of the standard model. You should have had all the ratios close to 1, whereas here we were finding the observed values of the ratios away from 1. And all of us at that time, remember, immediately started asking, is this the Higgs boson? because R should be 1 for all channels if it is the Higgs boson. And in the same issue of Physics Letters B, which actually had uncovered the earliest signal discovery of the 10 years ago, we also had this paper saying that the apparent excess in the Higgs to diphoton rate, new physics or QCD uncertainties, and our abstract really said that there are, most probably it is just QCD uncertainties. And I am personally very happy that it appeared on the same issue of Physics Letters B, which had carried the announcement of the discovery of the new boson. So this is my end of my historical recollections, and thank you very much for being polite and listening to me with patience.
Thank you, Professor, for the very insightful talk. So now I'll ask if you have any questions, participants. Please raise your hand if you have any questions.
Okay.
Okay, so if not, yes. No, I think he's clapping.
Just clapping.
Yeah. If not, then I had a question.
Yes.
So in the figure where you showed the different bounds on the, yeah. So there, I think there was this lambda which was once pi and once 2 pi.
Okay.
Yeah.
No, that's okay. I understand what you're asking.
Yeah.
So I don't need to show the slide again. It's
Yeah,
okay. Maybe I will show if others want to understand what we are discussing. So let me once again share screen. See, the point was that when you start talking about, the lambda equal to pi and 2 pi, what is the criterion of a theory becoming strongly interacting? That is the question that you want to ask. Is this theory strong interacting when self-coupling is pi, where self-coupling is 2 pi, or self-coupling is 1? So it is really asking the question because you don't have very well-defined criteria there. You can try to define criteria perturbatively, because in this regime when lambda starts becoming large, those criteria themselves are somewhat fuzzy, and therefore the idea was that you give a very wide rope to the strong coupling, to the regime where the regimes of lambda where theory will become strongly interacting. And the point you want to really see here is that even if you change it by an order of, by a pretty big factor, the upper limit on the Higgs boson did not change that much. You see what I mean? That if you are looking at 1 TeV, it was of the order of 350, 400 GeV, 750, within a factor 2. And you have to realize that when you don't have any other theoretical constraint on the mass of this object, even tying it down below, say, like 750 GeV was already an achievement, and that this achievement does not critically depend on the value of the strong coupling you use was a very important thought. Okay. You see my point?
Yes.
Okay. And that was and the other interesting thing was that this was also indicating that the triviality bound, which also and also the unitarity bound, which is around 751 TeV, that is again assuming, when you say unitarity bound, you are again assuming that there is new physics beyond 1 TeV or 10 TeV, and those bounds actually lie in the, these curves when extended to 1 TeV lie around 300, 700, 800 GeV, and the difference between them is also not too much. That is the point being made, that this is a robust prediction.
Okay.
In terms of these ideas. Okay.
Thank you. So, Professor Sudhir, do you have a question?
Yeah, Ravni, when you said before the discovery of the Higgs, there was only one sliver of region available. Is it purely from theoretical constraints? Also,
no, I said joint. You see, Sudhir, I made 2 statements. Let me go back to that. And that's, I thought I tried to, therefore I presented 2 different plots. See, this plot, okay, is all the hatches and the crosses are from, you can see the slide, right?
No, I think you had to share.
Oh, I have not shared it. Okay, that of course doesn't help. Let me share. Where is it gone? Yeah, share screen. Yeah, can you see it now?
Right. Yeah.
Okay. No, sir, I tried to be separated, so let me once again do it. Look here. Here, if you see all the hatches and the crosses,
Right.
they are all experimental.
Okay.
That you looked for the Higgs in this mass range, you didn't find it.
Right. Yeah.
Because the profile was fixed by the standard model, you knew the couplings, you knew the QCD corrections. So, in the framework of the standard model, a Higgs in this mass range up to here was ruled out, and beyond here was also ruled out. Now, overlaid on that is this blue band. The blue band is a combination of the precision measurements at LEP and the theoretical predictions of the couplings of the fermions with the Z and the W in theory. So this is a combination of experiment and theory, the blue band.
Right. Yeah.
And this band is pure experiment.
Okay. Yeah.
Now then I wanted to contrast this thin slither with this, which is a plot actually which I presented in a conference talk in December 2011, where here these are pure theoretical bounds which I had shown from the 2009 paper. These two black lines and these two lower vacuum stability bounds. Okay, and then the LHC had ruled out this entire red region. LHC had also, this was also experimentally ruled out, and then you are left with this slither from theoretical considerations. Now this is from pure theoretical considerations.
Okay. Yeah.
What one is saying is that this thin slither and this thin slither actually overlapped.
Okay.
So that was a great deal of relief, right?
Right. Yeah.
That from pure theoretical considerations, what we thought was still allowed was also still allowed by experiments. But if experiments close this, if LHC first run finally in July 2012 would have also removed this slither, then we would have had trouble, because then we would have brought this down all the way.
Right.
And that would have then said that standard model is simply not consistent.
Right.
That is really the point I wanted to make, and that's why I made these two plots separate.
Okay. Okay. Yeah.
Okay?
Okay.
Siddharth has a question. Maybe if it's a quick question, we can address it right now. Otherwise, we have to continue it later because we are short on time. So Siddharth?
Yeah, just a quick question. So, the way the two experiments excluded the regions for the Higgs mass. So, is it coincidence that the two experiments, the allowed region is such that where the actual mass of Higgs is to be, that part is
It's not a question of coincidence. The point is that LEP was not able to probe beyond 114 GeV. Okay? Because it could not have produced a Higgs beyond 100 with mass bigger than 114 GeV with enough rates. So 114 GeV was kind of the limiting value of LEP. Alright? Now the limit from the tevatron, which delineated only the region from 160 GeV onwards, that had to do with the fact that the tevatron kind of P bar P experiment was not able to see the Higgs clearly only in the range 160 to 180, where it will have decays into the virtual W pairs, which will produce some leptons or BB bars. In the intermediate region between 125 to 160, the really powerful final state was 2 photons. And for the tevatron energies, the Higgs production rates were not large enough for the inclusively produced Higgs decaying into 2 photons to give a signal. So tevatron was not able to probe in this intermediate mass range. Have I answered your question, Siddharth?
Yeah, thank
Okay.
you.
So that is actually therefore when LHC was designed, people had designed it such that no matter what the mass of the top quark is, because the production rates depend on the top quark, I explained that to you people, independent of the top quark mass, can you see the Higgs boson in the diphoton channel? because in the mass range 120 to 160 or 155, the really clean mode was indeed only the diphoton channel, and to some accuracy the di-Higgs, where the Higgs digging into a pair of a virtual and a real Z, producing 4 lepton channel. But the rates again for the 4 lepton channel were very small, and even the diphoton, since the branching ratio in the diphotons is something like 1 part in 10 to the 4, this was really required large production rates, and that's what required the LHC energy. Okay. All right, Kamelia.
Yeah, thank you again. So now we end session 1, and the next session starts from 11.
Should we take 10 minutes break, or just we should start it right away from 11, because it's already 11?
Maybe we take a 5-minute water break.
Maybe 5 minutes.
5 minute break.
5-minute water break, please.
Yes.
Okay. Okay.
So thanks again for your patience. Thank you.
I think this is the old timetable, I guess, because I don't see the title of the talk here.
Do you have a new one?
Yes, let me share.
You share it, yeah.
Maybe you can also Hello, is Professor Tirtho Astra here?
Yes.
Yes, he's here.
Could you please try to share your screen in the meantime? I will stop sharing and then you can start sharing.
Okay, so I hope
Yes, it's visible. Yeah.
दिसंबर वो रहना नहीं पड़ेगा ना, मैं दूर के रह के भी कर सकता हूँ.
Should we start?
Let's start at level 5.
Okay.
Yeah.
So probably you can start, right? It's 11:05.
I think we can start. Okay. Hello, everyone. Welcome to the second session of this morning. My name is Prabhat and I will be coordinating this session. We will have 4 talks in this session. So first 2 talks will be 25 minutes with 5 minutes for questions. And last 2 talks will be 15 plus 5. I will remind the speakers 5 minutes before their time ends. So please kindly adhere to the time. Please keep your questions till the end of the talk. If you have any question in the middle of the talk, please drop them in the chat box and we will take them in the end. So without any further delay, let's welcome our first speaker, Professor Tirtho Shankar Rai from IIT Kharagpur. He will talk about bottom-up composite Higgs phenomenology. So Professor Rai, over to you.
Okay. So I hope I am audible and
Yes.
my slides are visible, right?
Yes, perfect.
Okay. Okay. Okay, so let me first of all, thank the organizers for inviting me and for hosting such a nice event to commemorate the 10 years of the Higgs discovery. So the mandate that I got from the organizers is to speak about composite Higgs models. Of course, I won't be able to do a complete job with it, not only restricted by time, but also limited by my experience in this field. So essentially, but the discovery of the Higgs, 10 years back, heralded what we can call the Higgs era, where in this, scheme of things in high energy physics, there will always be a considerable attention to study the Higgs and its properties. And this is because the discovery of the Higgs was not a discovery of another vanilla, particle in the zoo of standard model particles, but probably it was our first glimpse into that notorious class of particles which are known as scalar particles. And this kind of non-trivially updated the standard model particles zoo. So one way to think about this is that before the discovery of the Higgs, the standard model particles consisted of vector bosons, but these were not any random vector bosons. They were all gauge bosons. And then there were the matter fields, which all happens to be some kind of chiral fermions. So these particles have a kind of an personal symmetry, which is of course inexact and spontaneously broken by electroweak symmetry breaking, but they are enough remnant symmetry for them to be protected from potentially dangerous stabilization issues from the UV. Now the Higgs is a completely different beast because it does not have any intrinsic symmetry that can insulate it from these by UV destabilizations. And this was of course identified long before the Higgs was discovered in 2012. And it goes by the gauge hierarchy problem paradigm. And there is, I would say, an industry or maybe even a civilization of models which have various ways of addressing these gauge hierarchy problems. So this cartoon over here shows some of these approaches. Now, if you look at the gauge hierarchy problem very naively, it basically arises because you are conjecturing the existence of a fundamental scalar in your theory. So I would say one very simple way to deal with this is to imagine that the Higgs that we have discovered is not a fundamental scalar at all. You can conjecture that the Higgs is a composite object which is ultimately built of some subparticles which may have their own symmetries, and therefore in the UV in place of the Higgs you will get all these constituents of the Higgs, and they may be protected from UV sensitivities due to their symmetries, like that happens to chiral fermions or gauge bosons. Okay. So and again, this conjecture that the Higgs is a composite scalar is not a revolutionary one. After all, in the 20th century itself, we discovered a plethora of scalar particles, which was later identified to be bound states of quarks and antiquarks, and were christened as mesons. So you can think of these Higgs as some kind of a bound state of more fundamental particles. Now, from the bottom up, the important difference between point-like fundamental particles and, let's say, a composite Higgs would be that the composite Higgs will have some extension in space. It will have a shape in space, and therefore you can ascribe an intrinsic length scale of the Higgs. Like it's like the size of the Higgs in space. And as soon as you have a length scale associated with that length scale, you of course have a mass scale, and let's call this mass scale as f of h, which is of course inversely related to the length scale of the Higgs, or the size of the Higgs. And this energy scale is what is known as the compositeness scale. So one way of thinking of this is the following, that below the compositeness scale, the constituents of the Higgs are able to confine and remain together, and you see the Higgs as the effective degree of freedom. But as you move the scale beyond the compositeness scale, the Higgs essentially kind of dissolves into its constituents, and therefore, if you imagine that none of these constituents are scalars anymore, this problem with scalars and gauge hierarchy problem just disappears, simply because at that scale there is no longer any fundamental scalar in your theory. So this is a very naive and straightforward way to address the gauge hierarchy problem, by doing away with any scalars in the UV. And what is also interesting and I would say minimal in this framework is that within the composite Higgs there is an intrinsic mass scale. That is the scale, this compositeness scale. So this is an intrinsic dimensionful parameter in the theory, and you would expect that everything in this theory would be proportional to this compositeness scale. For example, you would expect the weak scale, the Higgs mass, to be at the compositeness scale, because that's the only dimensionful scale sitting around. You would also expect that the masses of all the prions, which is the subconstituents of the Higgs, of this assumed composite Higgs, would also be at that same mass. So you are basically having a very flat spectrum where you have the Higgs, the weak scale, all the standard model masses, standard model particle masses, and the masses of these prions all at the same scale. And this is very predictive, and therefore has already been ruled out from the LEP data. We know that if you have a large number of these exotic resonances at the scale of the Higgs mass, and they necessarily should have standard model gate charges. After all, they will combine together to form the Higgs, and the Higgs has non-trivial standard model gate charges, so its prions will also have non-trivial standard model charges, and they would typically couple to the standard model gauge bosons and radiatively correct the 2-point functions of the Z boson and the W boson, and mess up with the electroweak precision data. Now, we have a lot of data collected at the Z pole in LEP, and from that itself, we find that this very, very overtly simple picture of composite Higgs, where the masses of these constituent prions, the Higgs mass, the weak scale, are all at the compositeness scale, does not work. They are simply ruled out by the electroweak precision data. And this is what you can see in this plot, where a chi-square fitting to the precision electroweak data is done, and you see the best fit values kind of pushes this ratio of the weak scale to the compositeness scale far below 1. So the best fit value is around 0.2 or even smaller. So you need a kind of a parametric hierarchy between the weak scale and the scale of compositeness, or the scale of where these new exotic resonances should show up. And this can be done, one way this can be done is to assume that the Higgs is not only composite, but it is also a pseudo-Nambu-Goldstone boson. A pseudo-Nambu-Goldstone boson would mean that the Higgs can be naturally parametrically lighter than the rest of the resonances in that sector. So this is how you can create this small hierarchy and survive the data from LEP. So just to, absolutely from bottom up, if you want to have a composite Higgs, you end up with this rather elaborate setup, where, of course, on one hand, you have all the standard model particles except the so-called composite Higgs. But then you have to conjecture this additional strongly interacting sector where there's some kind of strong dynamics, probably a strong gauge dynamics is going on that confines these preons to form the Higgs scalar, the composite Higgs scalar. But it should also produce more scalars and a potential that can spontaneously break some kind of a global symmetry of this strong sector G to a subgroup H. And you want to identify our standard model Higgs as one of the Goldstone modes sitting in this coset space of G by H. But this, of course, is, you get a composite Higgs, which is Goldstone, which means that it is massless. And of course, the information that we just discussed in the previous talk and what we learned on 4th of July 2012 is that, of course, the Higgs has a non-trivial large mass at around 125 GeV. So you have to somehow arrange for it, and that can be done if you promote the Higgs to becoming a pseudo-Nambu-Goldstone boson, which means that you need some mechanism to explicitly break this global symmetry of the strong sector. One very elegant way of doing this is to imagine some kind of a linear mixing between the strong sector and the rest of the standard model states. After all, the Higgs at some stage have to talk to the standard model particles and drive electroweak symmetry breaking. So this connection is inevitable, and you can do it by having a kind of a linear mixing, and this is what is known as partial compositeness. So for this linear mixing to go through, you now need the strong confining dynamics to not only create the composite Higgs, but also it has to confine and create composite operators. If you like an analogy, it would not only need to create the mesons, but it would probably need to create, things like baryons and, vector mesons and things like that. So you need this confining dynamics to also create these kind of vector operators that can linearly mix with the standard model fermions. And these, strong operators are like saturated by some composite, resonances of the strong fermionic composite resonances of the strong sector, which are collectively known as top partners. Again, it is given that if you have a fermionic operator, you can just combine them, let's say with a gamma mu or whatever you want, and create a vector-like operator of the strong sector. And these vector-like operators will be saturated with vector bosons, composite vector bosons, which can linearly mix with the elementary vectors bosons of the standard model. And these are sometimes collectively called the gluon partners. So in some sense, the simplest, if you pare it down, the bare structure of any composite Higgs framework would require multiple length scales. Okay, so at one end you will have this pseudo Nambu-Goldstone Higgs, whose mass is radiatively generated due to this explicit breaking and linear mixing at, of course, 125 GeV, which is at, let's say, the weak scale. Now, this has to be parametrically lighter than the composite resonances, which is the top partners and the gluon partners, just to survive the electroweak precision data. But interestingly, if you take such a scenario and do the computation for the Higgs mass, its dependence on this resonance masses and the compositeness scale is like the one shown on this slide, that the mh square goes like mt square, which is the top mass square, times these resonance mass square divided by the compositeness scale square. Now, since we know now that the Higgs mass is lighter than the top, you need also now another hierarchy between the compositeness scale and the masses of this composite partner, which is why you have this third scales included, which is basically the cutoff scale of the theory or the compositeness scale of the theory, and the composite partners. They also have to be separated, but this hierarchy is not very problematic. After all, these are all kind of gauge bosons and chiral fermion. Therefore, you can sustain this hierarchy from any kind of UV destabilizations. So this is the bare picture that you have, and the idea, if you want to now try to search and identify whether the discovered Higgs is a elementary object or a composite object, these are the targets that you have. You have to either look for these composite partners, the top partners or the gluon partners in a collider experiment, or you have to look into the Higgs data and check whether you find signs of a pseudo-Nambu-Goldstone boson and a pseudo-Nambu-Goldstone composite Higgs boson in those data. So these are the two handles that you have. So if I just like try to enumerate them, these are the three approaches that you can take to probe a PNGB composite Higgs model. Okay, so you can either think about searching for top partners at colliders. Some of these top partners would evidently be colored. They will have color charges and therefore profusely produced at hadron colliders like LHC. They might have exotic standard model charges, therefore producing stunning and visible signatures. So that is one approach. The other approach is to look into the Higgs data, and in this case there are two things that you can search for. Number one is that since the Higgs is a pseudo-Nambu-Goldstone boson, it is non-linearly realized, and this non-linear realization of the Higgs means that even at the weak scale, the Higgs couplings will show a pattern of deviation from the standard model predictions that you can then search for. The other more intrinsic feature of compositeness of the Higgs is the fact that the Higgs has this finite size, and which would mean that its reaction to any other fundamental scalars of the standard fundamental constituent of the standard model will be a structure function, which would mean that these couplings will have very aggressive dependence on the momentum, more than the usual Higgs standard model couplings, where the these couplings have only soft dependence on momentum scale, logarithmic dependence coming from renormalization group running. But if the Higgs has a finite extent, it would have a more aggressive scaling with momentum, and one can search for them. So in the next, 5 minutes or so, I ask for your indulgence where I try to share some of the work in these three directions that we have carried out in our group, mainly led by Shayan Dasgupta and Obhik. But these are just like sample, efforts in a more broad category of studies, vast studies which have been done in these three directions to figure out whether the Higgs is composite or not. So the first, and I would say the most simplest low-lying fruit, is to search for these composite resonances. These composite resonances may be, as I said, they may have color charges, and therefore they can be produced even at LHC and all future colliders, and you can then check whether these resonances show up. A small comment here is that these resonances, remember, are a product of a strongly interacting dynamics that creates the composite Higgs. So there is a very large non-perturbative coupling that is floating around. So it is very easily possible that these resonances may have very large decay width, and the decay width may be so high that the naive narrow width approximation may start failing and may not capture its true phenomenology at colliders. So for example, what I show here is some limits on a top partner, where along x-axis I have the top partner mass, and along y-axis I have the decay width to mass ratio. The solid lines are the lines, the dashed lines are the lines that you get by assuming that these limits come from a narrow width approximation of these top partner resonances. Whereas for this solid line, we have assumed that the propagators of the of these resonances are the full 1pi summed propagator, without actually taking the approximation of replacing the loop by its decay width. So if you take the full momentum dependence of these 1PID summed propagators, you get this solid lines. And as you can see, as soon as this gamma by m hits a 20% or so level, the solid lines and the dashed lines deviates a lot, and this is something that one has to carefully model in case of this collider searches for this composite strong resonances. So these are some again some sample limits on these top partner masses. The takeaway information is just the following: that there's a plethora of these top partners which you can which can come up depending on the particulars of the strongly interacting sector, like what is the global symmetry G, what is the the subgroup H, and so on and so forth. So depending on these details, you can have a variety of these exotic top partner resonances, and they usually would also come with colored vector resonances, both of which can be profusely produced at the LHC. And since we have not seen any sign of them, they lead to aggressive constraints.
Excuse me, you have 5 minutes. You have 5 minutes.
Thank you. So for example, the present limit on this top partner masses range around 1.5 TeV, whereas the typical limit on the vector partner, the gluon partner masses is around 2 TeV or more. So you can clearly say that we are bleeding, fine tuning even in these composite Higgs models, like probably every BSM scenario. However, one should also note that if you really discover these exotic top partners and gluon partners, it would of course be a discovery of new physics, but you cannot still answer the question about the compositeness of the Higgs directly. This will only be an indirect evidence of something that may be related to composite Higgs, but this inverse problem is complicated by the fact that there are other plethora of motivated BSM scenarios like extra dimensions, extra chiral generations, and so on and so forth, which can have all these resonances, and then it's not easy to differentiate between them. So probably a better way to think about this is to look into the Higgs data and study whether there is this kind of a deviation of the Higgs couplings from the standard model prediction. So one of these deviations, which will always be present at every scale and therefore also at the weak scale, but comes from the fact that in these models, the Higgs is non-linearly realized. So you would see that the coupling of the Higgs to all the standard model states, the standard model fermions and the gauge bosons, would show a pattern of deviation where the deviation is a function of this ratio of the weak scale and the compositeness scale. So one can search for this telltale deviation from the standard model states and can identify whether the Higgs is non-linearly realized or not. At present, of course, we do not see a large deviation, as was pointed out in the last talk, and you can only put limits. And I do not want to labor this point that the limits is again pushing this hierarchy between the weak scale and the compositeness scale even further, which would mean that you still have more fine tuning. But if you go and the LHC is probably expected to study these Higgs couplings at the weak scale at around 10%, maybe for some channels, and worse for others. And this may not by itself be enough to identify such a pattern of deviation and therefore identify a composite Higgs. But we will do much better in future Higgs factory. But again, a caveat that if we discover such a pattern of deviation, we would still be talking about the fact that the Higgs is non-linearly realized, and that's all. Of course, there is examples of BSM model where the Higgs is fundamental but still non-linearly realized, like the twin Higgs and so on and so forth. So this will be a discovery of the non-linearity, but still we cannot probably conclude that the Higgs itself is composite and has an extension in space. So, without beating around the bush, in some sense, the real telltale signature that the Higgs has an extension in space is to identify the structure functions of such a composite Higgs with other elementary states. As we know that if the Higgs has a finite extension, the coupling with fundamental particles will no longer be coupling constants having logarithmic dependence due to the renormalization group running. It will have a more aggressive dependence on the momentum transfer because they will be structure functions. So this is kind of nicely shown in this cartoon at the bottom of this slide. So what we have is that along x-axis, let's say you have the scale, of a Higgs-mediated process, and along y-axis you have the Higgs coupling extracted from that Higgs-mediated process. So if you have a standard model Higgs, it will give you some value, and it will have a very slow logarithmic scaling with this scale. So let's say in the range of interest in present and future collider, this would appear entirely flat. If now you have a non-linearly realized Higgs sector, there will be a finite shift in these couplings, but that finite shift will still scale very, very softly with the momentum. Whereas if you now have a composite Higgs, which has a non-trivial extent in space, these couplings will have a very aggressive power law dependence on scale, and you would expect to just drop off quite before the compositeness scale. After all, at the compositeness scale, the Higgs itself dissolves and these couplings do not cease to exist. So it will very quickly kind of fall off to small values around the compositeness scale or before it. So the real way of trying to figure out whether the Higgs is composite or not is to find out whether its coupling shows such an aggressive dependence on the scale. Now, the problem here is that what is this dependence on the momentum of these couplings? Because after all, this is strong non-perturbative dynamics of the sector which produces the composite Higgs, and it is not easy to model them with perturbative quantum field theory. We know that if you now let's say focus on the Higgs vector boson couplings, the HVV couplings, they are these very nicely behaved numbers, gauge couplings, if we talk about elementary Higgs. In the case of this finite width composite Higgs, they would become some aggressive, momentum dependent object. But now the question is how to model them. There are many approaches to this. One can take a phenomenological approach. One can use holographic dualities with gauge Higgs unified scenarios in higher dimensions. One can use lattice theory. In a recent exercise, we tried to model these structure functions using, let's say, the leading results from a large N approximation. So we are assuming that this confining dynamics is some SUN gauge group, which produces this composite Higgs, and this N is large, and you take the leading effect from there. And then you model what this structure function would look like, at least the leading dependence on the momentum would look like, and then you can go ahead and try to do some kind of phenomenology. For example, we looked at the associated production of such a Higgs with a Z, where the Z decays to a pair of lepton and the Higgs decays to a pair of bottom quarks, and you assume that this Higgs Z coupling is not a number, but now this complicated momentum dependent structure function. And what you end up getting is something what is shown in this plot on the right. Along x-axis, I have the center of mass energy, and along y-axis, I have the cross section. So the red line shows the typical secular decline of these cross section for elementary Higgs due to the 1/s suppression. Whereas if you use the structure functions, you end up getting these blue and pink lines, which shows the very drastic deviations, and the peaks typically happens at when you cross the mass scales of these underlying resonances. So every time you pass those resonances, you get a kind of a peak. So the way to search for them in a real collider experiment is to, one way to do it, let's say, is to do the following, is to look at the tails of kinematic distributions of various Higgs-driven processes. So you take a Higgs-driven process and you look at the kinematic tail where the Higgs is pushed off shell. So as soon as the Higgs is pushed off shell, if it is if it is a composite Higgs, its couplings will change drastically, as opposed to an elementary Higgs where it will hardly change at all. And these drastic changes in the tail will show up as a great deviation in these kinematic distributions. So these are the plots that we kind of example kinematic distributions generated using that associated production of Higgs channel, where the Higgs decays to a pair of bottom quark and the Z decays to a pair of lepton, and we have created all kind of kinematic quantities using this end state entities. And the red line are the lines that you would get for an elementary Higgs, and let's say the blue lines that you can see in these plots are the ones that you would get from a composite Higgs. Now, instead of going into the details of what these kinematic observables are, what we can clearly see that if you look into the tail, every time these kinematic distribution for the composite Higgs expectedly starts deviating from the standard model prediction. So one way to really answer the question whether the Higgs is composite or not is basically to study the Higgs in its off shell condition and look at processes where the Higgs is off shell, and probably look into the tail of various kinematic distributions. Okay, so now this program, if you want to really study the Higgs in its off shell condition, you would now need a lot of leg room, a lot of energy available to you, so that you can push the Higgs off shell. And therefore, in this direction, probably you would hope. Of course, you can do certain things with the LHC itself, the high luminosity LHC, but the proper direction for trying to study for this is to basically have more energy at your disposal, that you can really push the Higgs off shell and then study the various properties of that off shell Higgs, and specifically look at the kinematic tails. And that would kind of tell you whether the Higgs couplings have some aggressive momentum dependence beyond the usual logarithmic scaling, and in some sense that would be a telltale signature of the fact that object. So thank you for your patience, and I think I've already exhausted my time, so let me kind of wrap it up. Thank you.
Thank you, Professor, for the wonderful talk. If anybody has any questions, please go ahead. We are already running short on time. So I can see 2 hands raised, 3 hands raised, sorry. So Professor Sudhir, if you could.
Yeah. What is the limit you can have for F on F?
Limit you can have on F? F means the composite scale? Composite scale, yeah. Okay, sorry. Let me try to again share my screen. I don't know what happened. So, can you see my?
No, not it. Yeah.
Yeah. So of course you can push this scale F up as you wish.
Right.
But then you would pay with fine tuning. That is basically the issue. But the fine tuning is like the ratio of the scale F and the weak scale. So in principle, you can just keep pushing the F up, and you have to pay in terms of fine tuning. If your question is related to what is the present limit on F,
right.
Okay. So it is around, if you take just the precision data, the limit on F is lower. It is around 700 or 800 GeV. Now, depending on the details of the UV completion of your model, you will have different resonances. So these resonances can then, make your theory more fine-tuned and push this scale F beyond 1.5 or 2 TeV.
Okay, so it is still a natural solution to hierarchy problem?
Well, Well, okay. So I would say this has the same level of fine tuning as, let's say, the most natural version of supersymmetry. So it has a lot of fine tuning already because we do not see these resonances, and that is like at the same order as standard model. I wouldn't, it's not better than the standard, not better than supersymmetry. Sorry, supersymmetry, not better than the MSSM. It's at the same level.
All right. Okay. Thank you.
Siddharth, can you please go ahead and ask?
Can I ask my question?
Siddharth, can you please go ahead and ask? If not, then Professor Shubhaditya.
Yes, Siddharth can type the question in the chat box. You can take it.
Hi, Tito. This was a wonderful talk. I just have a question regarding the kinematic distributions that you showed, which distinguishes the composite Higgs to the fundamental ones. And I was wondering that what are the class of kinematic variables where this distinction in the tail actually can show up? Because I see a bunch of invariant mass distributions, and also I see the transverse momentum of the leptons and bottom quarks and so on. So can you comment on that?
Yes. So I would say that, practically we tried with all these, things that you can construct out of those 4 things in the final state here. There's also another study that was done by Tao Han, another by Gustav Boardman in a similar fashion. And it seems that probably, any kind of, if you take the Higgs sufficiently off shell, and then you look at any Higgs mediated process, nearly all of these kinematic distributions, would start showing deviations in the tail, right? Because
Okay.
Yeah. So the answer is that everything that we tried to construct in our example showed deviation when you get the Higgs off shell, and probably this should be generic. But okay, I cannot.
Yeah. So it is immaterial whether you look into the decay products of the Z or of the Higgs or a combination of them that actually shows up in the at least in the tail of the distribution.
Yes, that is because you see this, if you see the process in this slide, this non-trivial momentum dependence in the cross section shows up before the, either the Z or the
further decay products are considered.
Yes. Right. So you already have this, new, modulation with momentum inbuilt in this, cross section or the differential cross section.
Okay.
Now, whatever you do, would show deviation from the standard model behavior as long as you are sufficiently off shell.
Okay, all right. Thank you, Peter. Thanks.
Professor Ghosh, could you please unmute and ask?
Peter, it's nice talk. So just a quick question. So in one of the slides, you actually showed a relation between the Higgs mass, the number of colors, the top, the mass of this new quarks, and the scale.
That's right. So let me try to go there. Yeah.
This
yes.
formula. So just so roughly, I mean, if I consider the standard model, the mass of the Higgs is about 70% of that of the top, roughly. So from that viewpoint, like, is there any wildest possibility like this MQ and the FH of the similar order, like both in the ballpark of a TeV and not like 10 times larger?
Well, so you see MQ square by FH square is like MH square by MT square, right? So this is basically what it is, right? So you can of course tune the MQ to be slightly lighter. So okay, let's say this: there is the weak scale, there is a compositeness scale, and we know that the exotic top partners and vector partners has to lie somewhere in between. It has to be an order of magnitude heavier than the Higgs because of this PNGB suppression.
Sure.
But where it is, whether it is closer to the cutoff or you can push it down, is kind of a choice and depends on the details of the UV completion of the strong sector that you want. So what I'm showing here, where the composite partners is at 1 TeV, is just to make it more, let's say, interesting in terms of collider.
Okay. Yeah. Okay. In terms of the BSM searches. Okay.
Yes. Yes.
Okay. Okay. So, and this NC
but
is,
as you said, you can tune it to be closer to the cutoff.
Okay. Okay. And this NC is the effective number of color. Everything below that scale.
Yes, so NC is just, so these are generated by the Coleman-Weinberg potential. So NC is just the color charge of these, exotic resonances which are there in these loops. Okay.
Okay.
So you can consider them to be 3, let's say, for a kind of a number.
Okay. Thank you, teacher.
Okay.
Professor Shivani, could you please ask?
Hello, Tirtha, can you hear me?
Yes.
Yeah, so this is regarding the plot. Can you please go to the plot?
Sorry, which plot?
The last slide, I think you had, those distributions actually. Yeah, sorry.
Okay,
Yeah, so actually, I think this is not a new question, but I just wanted to understand that usually the study that you have, they are used to place bounds, right, on the parameters, whatever you have. I was just wondering that these plots, in the context of experiments, suppose that, I mean, instead of talking about placing bounds, if in nature these couplings indeed exist, okay, does experimentally it means that I will find in my experiments, which is say bounded by some energy, center of mass energy, I would find actually more events with high PT and high invariant mass? This is one question. And connected question is that, is it perfectly fine with the unitarity in that case?
Okay. Well, okay. Thank you for this question. So first of all, let me tell you that these plots that I'm showing are not mounts, right? These are just like signal predictions. Okay. So you're absolutely correct. This is what this kind of a framework is predicting. It is predicting that if you go ahead and able to access this tails of this kinematic distribution at LHC or maybe at some future collider, and you see that in the tail there is a kind of a deviation, you see more events with high PT and so on and so forth than expected from the standard model, it would be a kind of a signature of these composite Higgs scenarios. Okay. Now coming back to your question about unitarity, so so there is many way, let's say, to model the these structure function like coupling between, let's say, a composite Higgs and elementary, in this case, Z boson. Okay. One popular way to deal with this is to write down a kind of a chiral Lagrangian for the composite Higgs and then extend it, expand it and write down an effective field theory. A very popular approach to this is what is known as the strongly interacting linear Higgs. And this, if you see in this plot, this black dotted line is this, prediction from the Silch framework. Now, in this case, as you said, that it will start violating unitarity because the EFT will at some time fail, and then you have all these issues with unitarity. One of the reasons why actually modeling these structure functions carefully using, let's say, large N or lattice results is you end up getting scenarios which are unitary. Okay, so while it might look in this plot that the blue line is blowing up at high scales, but if I had extended this to even higher energies, you would see that the blue line at some stage would go below the red line, and in the end, unitarity will be restored. So the way we have tried to, model these structure function like couplings is to keep unitarity in mind, and these theories are unitarity in the high scale, and that is also true for this kinematic distribution. So I'm again zooming into the range where, of course, these deviations are highlighted, but at some stage this will fall off, and of course, if this theory is correct, then there is of this compositeness scale where the Higgs will just no longer exist, and at that scale these coupling plots will go to 0, and again unitarity will be restored. I hope that kind of answers your questions.
Yeah, thanks for the answer. Yeah.
Professor Godbole, could you please and ask?
Thanks. Actually, most of the discussion that happened now has more or less covered the extent of the comment that I wanted to make. But going back to Shubhaditya's question, I wanted to say that generically, when one has momentum dependent couplings, it is the PT distributions that are the most robust under the predictions. The invariant masses, both from the point of view of experimental reconstruction and also because of the cancellation among the momentum behavior of the different individual particles when you calculate the invariant mass distribution, the most robust one are PT. I mean, as you can see that delta R, of course, is more or less talking about the how do you call, getting everything either, the relative orientation, and therefore that is reasonably distinguished, and so is the PT. But invariant masses usually tend to get smeared quite often from other effects, and so this was just I wanted to answer the question that Shubhaditya had raised, and then I was going to make a comment about unitarity, but then the discussions already took care of that. Okay. So thank you very much for giving me the occasion to talk. Thanks.
Thank you. That is the answer. Yeah, thank you.
Thank you. Okay. Thank you again, Professor, for this wonderful talk and answering all these questions. So we are running short on time. So let's move ahead.
Okay. And thank you for giving me this opportunity to make this presentation. So let me just stop sharing now. Is it fine?
Yes, please.
Okay. Now I don't know how to stop sharing. Okay, thank you.
Yeah, so next speaker is Professor Joydeep Chakrabarty from IIT Kanpur, and he will talk about EFT to sniff out heavy scalars. Professor Chakrabarty, if you could please unmute and share your screen.
Am I audible?
Yes, you are audible.
Yeah, so I have shared my screen.
Yes.
So actually I'm traveling, so I prefer to switch off my video. I mean, it's allowed actually. I can share my user bandwidth.
You can turn off your video if you want.
Okay, thanks. Yeah, because the bandwidth is not good.
Yeah.
Let me know when I can start.
You can start.
Okay. So yeah, so before I start, I would like to thank the organizers for organizing this wonderful this symposium, one-day symposium after this to celebrate the Higgs discovery decade. So today I'll talk about not exactly about the Higgs, but something related to Higgs. So as you know, that Higgs is a scalar object. So now after the discovery of Higgs, we have been a little bit greedy, and then we posed the question that if in the nature there's only one Higgs, or there could be multiple other heavy scalars. And if that is so, and as we have seen, there are lots of phenomenological models, and most of them actually contain non-standard model heavy scalars. So the question actually, if we have those kind of scenarios, and then what would be a good or nice framework to realize their presence. So the thing that I'm talking about today, I would like to use EFT, effective field theory, as a kind of a sniffer dog to smell the presence of heavy scalars if it is around the corner and not far away from us. So yeah, so before I proceed, I would like to post the bigger question that we want to address. So the thing is, basically, we have seen in the literature there's so many different kind of phenomenological models, right? And because they have different kind of interactions, different kind of symmetries, different kind of particles, and so on. So even when you have the data, it is really difficult to make comment on which one is good, which one is bad, or make a kind of a comparative analysis, and so on. So the bigger question that we want to understand, can we come up with a framework using effective field theory such that we can bring most of those scenarios on a platform where we can really compare them in the sense because they will be described by the same kind of symmetry, by the same kind of particle content or degrees of freedom, and so on. So for example, let's say look at this cartoon. So where you have different kind of BSM theories, okay? And you can see that the small phi stands for the standard model particles, okay? And this capital phi are the basically heavy non-standard model particles. And here I'm saying heavy in a sense that they can be integrated out and EFT can be evaluated with this assumption. So now there's a two way to look into this thing. So one, we have this known theory, which is the standard model one. We know its symmetry, including the internal symmetry and the space-time symmetry and so on, and we know the particle content. So what we can do, if we are blind to the kind of easy theory, we can construct effective operators using that information about the particle content and the symmetry, and we can get at different mass dimension, the finite number of effective operators, which are non-redundant basis. Now, for example, let's say this is the island of some, for example, let's say dimension 6 operators. So this is the bigger island that you are creating using this information about the low energy theory. So now what we are looking at about this different theories, we are isolating those heavy modes and we are integrating them out. And once you integrate them out, basically you are writing this theory in terms of an effective theory. And because you are integrating out, you will generate some kind of effective operators which will capture the footprint of those heavy modes interactions. So then eventually you will get a kind of a subset of this within this island. So this island is the biggest one, and in whatever be your theory, you cannot overflow this island. That's the idea, right? So now you have a different theory and you get a different patch of these islands. And because there will be some kind of similarity in the interactions pattern, there will be some overlapping zones. That means two different theories after being integrated out, they may lead to some set of operators, and some of the operators could be common thing. So in this way, we can create all those patches. So now, if you can generate all these islands, then we can look into these islands, and then we can try to understand the correlation among these operators and the observers, and from there we can say something. And that's basically the idea. Now, while doing this analysis, there are two things are very important. One is basically how to integrate out those different kind of scenarios and how to get those bigger islands. So that's the more complete theoretical constructions, and that's why we have divided our prescription basically in two parts. One is the methodologies. So these are the basically small developments to achieve those necessary methodologies or the equipment. And once you perform all these methodologies, you get all the operators and all those things, then in the light of the data, you have to perform the analysis. And these are the papers where we have performed the detailed analysis using those EFT things and the comparative analysis and comparative analysis for different kind of scenarios. So for today's talk, I'll mainly focus on this construction methodologies. And what I'll do, rather than going into much detail about those methodologies, I would show you the glimpse of those individual small baby steps that we have taken to reach out and this full thing. And if you and after the talk, if you're interested, actually you can talk about it a little bit more. So yeah, so the way I'll be following up this talk, first I'll talk about the bottom-up versus top-down approach of effective field theory, and then I'll show how different kind of BSMs can be realized in terms of effective field theories, and then I'll use the observers, basically the low energy observers, and which are nothing, but I'll treat them as a set of operators, and I'll use them like a response screen, and how those set of operators will help us to discriminate different kind of theories. And that's what lead to the classification of BSMs. And then I'll move to the fact that in the other way around, if we know if you're interested for some particular operator, then how do you know that what kind of BSM scenarios can offer you that kind of operators instead of having a blind hunch? So how to do that reverse engineering? And related to standard model Higgs, if they couple with some kind of non-standard model heavy fermion and having some kind of CPU halation, how to capture that effect. And then I will talk about the future direction, that if we are fortunate enough and find out new particles, then how this whole calculations, which is based on kind of SNET, can be modified and need to be modified. So yeah, so the bottom-up approach, so what we have as an information, you know the standard model as a low energy theory, you know the particle content and the symmetry, and based on that, what you are doing, you are actually constructing these effective operators starting from dimension 5. And there are basically irreversible interactions, and then these are the blobs which actually contain the effective operators. Now in this construction, you do not need to know the exact nature of the UV theory. And that's why when you write down these effective operators along with this irreversible part of the Lagrangian, you add those Wilson coefficients as the free parameters. And actual origin of those Wilson coefficients are not known, and that's why you add one operator, you are basically adding one extra free parameter in your theory. And that's why it's like in the bottom-up approach, the invoking more and more operators is basically including more and more free parameters in your theory. But the other way, what we can do, you start with your favorite UV theory, and that UV theory you can recast in terms of like a pure standard model like scattering, and then there will be pure new physics process, and then pure standard model process. So now, if this new physics propagators, this can be anything, and if this is a basically heavy particle, you can integrate that out, and you get this effective operator. Now, unlike the previous one, here actually you are starting with a UV theory, so you know what kind of interaction it is. So, and also what kind of particles are there. So that's why here also you get the set of effective operators, but here the Wilson coefficients are actually the function of these BSM parameters. So that's why you may end up with a multiple effective operators, but those effective operators, all of them will eventually function of those very limited number of BSM parameters. So in the theoretical point of view, in this particular case, the Wilson coefficients are related to each other, unlike the previous one, because in the bottom-up approach, we do not know how to relate different kind of Wilson coefficients. And because we will be dealing with many theories, so it is obvious that it will be difficult to do everything by hand. So that's why we prefer to come up with an automated tool, and that's why we develop this codec. And this codec is basically offers you one loop Wilson coefficients once you identify what are the heavy modes and their interactions. So it gives you the Wilson coefficients, and you get the Wilson coefficients as well as the one loop level. And also it helps you to run those operators down till the electric scale, and such that you can compare them with the low energy data. So far, it can actually integrate heavy scalars. And it can deal with the heavy light mixing for the scalars, and all the intricacies like equation of motion, different kind of identities, integration by parts, all are taken care of. Okay, heavy fermions also can be integrated out, but only that multiple heavy degenerate fermions. And we are adding some more features with it, like for example, in the loop, if you have a fermion and the scalar, which is a mixed statistics kind of diagrams, and also the heavy light fermion mixing, and also to automate the dimension 8 computation up to 3 and 1 loop. And for the bottom-up approach, you need to come up with a proposal where you can construct those effective operators using the symmetry and the particle content. And for that, we have developed this group invariant polynomial construction, which may allow you to work with any kind of degrees of freedom and get the effective operator of any mass dimension. So yeah, so now once we have these things, so what we are doing, so once you have some low energy theory, using this grid, we can construct this bigger island. And because we have this codec in our hand, so you can have 20, 30, whatever number of BSM theories, you just identify them, and you just identify the heavy modes, you integrate them out, you identify those small patches, and basically that's why you are ready to compare them, because we have brought all those theories on the same footing. Yeah. So now, as I was telling, that we have different kinds of observers, but for example, we will choose the electric fission observers and Higgs signal state. Okay, so here, if you look at these observers actually can be recast in terms of these effective operators. So the leading order EWPO, we have these effective operators. Okay, and if you go for the NLO corrections, and then you have these and these many operators which are offering contributions to EWPO, and also the Higgs signal strength actually contain part of the operators which is EWPLO and NLO1. And also on top of that, we have these additional contributions. So now, once you have your favorite theory, what you can see that what you integrate out the heavy modes and you see what are the subset of the effective operators that you are getting, right? And then you can look into this chart and immediately understand that, okay, what are the lower energy observers will be affected by those effective set of operators. Now, when you integrate out, you don't really get only these operators, but also you get some additional operators. Some of them are also BL violating, and there are some additional operators. So we are clubbing them as additional operators, but one can certainly come up with some new observer, and these operators will belong to that set. So these we'll use as our response screen. And to understand how do different BSM theories behave in presence of this screen. So I'll skip these dimensions operators because this is well-known. Yeah. So now about the BSM classification, what we have done actually, we have started with a very simplistic scenario, and we have assumed that at a single point of time, your standard model is basically extended by one heavy scalar. Okay, and that heavy scalar are basically the charge of the heavy scalars are basically motivated by different kind of phenomenological models. So, for example, like it's a single scalar, it's a complex scalar, real triplet, complex triplet, doublet, quadruplet, and so on, which are basically the color singlets. And also, you have different kinds of leptoquarks in the literature, and which are basically the colored object. So, these 15 models are basically we are interested in to display what we are trying to convey the message. So now, before showing you the result, let me give you the idea of the heavy light and all those things. So you can see when we are talking about the T-level generation, that means basically in the UV diagram, your heavy particle appears in the T-level propagator. When we call the heavy loop, that means in the loop diagram, all the propagators are basically heavy. But sometimes it may happen that in the loop diagram, you have a heavy and the light mixing, and that's what we call a heavy light mixing. Now, based on this nomenclature, what we have done, we have employed codec and we have invoked individual models, and we integrate out these individual heavy modes. Now you can see that once you integrate them out, these are the non-zero operators that you are getting. So this cross means that this operator is not being generated up to one loop. Okay. So this QAG operator will be generated through the heavy light mixing, but in case of real triplet, that operator is being generated at the T level itself. So in this way, we have computed and classified the generation or the emergence of those operators, whether it's a tree, whether heavy loop or heavy light loop. So yeah, and this is also like other set of operators are being generated for all these models. So you can see on total 47 operators at max we are being able to generate up to this one loop calculation. Right. So now we'll see that how this will respond. So the idea is basically we borrowed the idea of this thing from the optics. So let's say you have a magic screen, and the magic screen actually can club the rays of different of the same frequencies. So then what will happen is if you're passing light that contains different kind of frequencies through this magic screen, then on the right side after being passed by, so in the you will see the patches of different lights of same frequencies. So that's we are getting the idea here. So you start with these 15 models. We have integrated out those individual heavy fields, and they offer you different set of effective operators. Okay, and then if you use this electric observability model as my response scheme, and I pass them to this thing. So what I'll see that the kind of operators that are affecting this observable, that actually is being, you see these 7 models to be in the same footing. That means these models may contain different operators, okay, but it depends on what kind of screen you are using. For this screen, actually these models are containing the exactly same kind of operators. on the same basis, you will get a different class of operators which actually differ from this class by at least one operator. That means there will be only at least one operator which affect your this observable, which may belong to either class 2 or class 1. It can be more than that also. And that's why looking into these observables on the set of operators, we can get this 4 non-degenerate set which contains all these 15 things. Now we'll use the same idea for others. Scheme. Let's say we are using the Higgs signal strength as our scheme, and then we'll see we get 6 different in such club, and each of them can contain degenerate models. Like class H1 cannot discriminate this H2 delta 1 and quadruple model based on the operators are affecting that HSS or the Higgs signal strength. And we are repeating this same task for different observers and trying to understand that how they are being classified or being clubbed under different set of observers. Now it will be interesting to see that if we place this scheme one by one rather than using one at a time, and then this is what we are getting. So you start with these 15 theories, and then you place first this model, and then you see that okay, these 2 models are discriminated from there, and then you get this kind of operators, and then so on, and you put all the spins one by one. And if you can design some kind of observers in the name of additional operators and include the BLV, and then you see that you can actually see the distinct feature of different models, and that's why all of them contains at least one feature, one smoking gun feature, which is absent in the other. But again, you cannot get all of them, make them non-degenerate, because you can get this kind of left clock scenarios, which even you use all the observers, you will get them to be respond to be in a degenerate manner. That means if the theory is like contain this or this or this, based on these observers, it will be difficult to discriminate them. So now, without going into much analysis on all those things, what I try in the reason I put this plot to show you that difference when you perform the analysis bottom up and the top down. So as I was saying, that in a bottom up approach, what you do actually include those operators, and they are actually free parameters. So you basically increase the degrees of freedom from the fitting point of view. So that's why in a model independent approach, you get this whole allowed range of parameter consistent with the input data. But when you use, let's say, use double model or quadruplet or the compressed model, so all of them offering the exact 9 operators. Okay, but here those 9 operators are actually function of 3 parameters. So now, and they are also related to each other. That's why when you come from a top-down approach for a given theory, the allowed parameters space, this is so minuscule compared to this larger thing. So the practice that most people follow, that using this MET analysis, we allowed take the allowed range of this Wilson coefficients of the parameters and directly use that for the BSM. That is somehow slightly misleading.
Professor, you have 5 minutes left.
Okay. Yeah. So now, as I was saying, that if experimentalist tells you that if you have some interesting anomaly, and that anomaly can be identified by some kind of operators, then what will you do? This is the generic approach that we have talked about, right? But on the other hand, from the experimentalist colleague, if you come to know that okay, this is the observer showing the anomalous behavior, then you try to identify what are the SMET operators are actually can offer you that additional contributions, and then using our method, we can unfold that, and then using the symmetry argument, we can identify what kind of heavy fields can lead to this kind of operators. Because once you identify that, then automatically you can build your EV model, and then instead of having a blind hunch, you can actually perform the realistically and data-driven model building. And this is some sort of one example that okay, start from a theory effective operator and how do unfold, and then identify what kind of heavy fields actually gives you this kind of operators. Okay, so now we talk about the CP conserving sector, and now it may happen that you have some kind of heavy fermions, especially the vector-like fermions, and that may couple to standard model Higgs, where you can have a CP violations. Okay, and then what will happen once you integrate these heavy modes, you get CP violating operators. So you can see the CP odd operator is basically counterpart of the CP conserving operators. So what we have shown and computed that once you have this kind of interactions, how this can lead to partly CP violating operators or CP odd operators, CP conserving operators. And that's the first time we saw that you cannot just include CP odd operators without adding the CP even operators, because you cannot have any diagram where you are generating all the CP odd operators, because these eventually will be side by side always. So the analysis there you are doing only for the CP odd observers, but you have to keep in mind to adding on the counter partner of the CP even operators and the corresponding observers, and that's why you get much better constraint on them. So yeah, so this is all what I talk about is basically based on the standard model as a low energy theory. But if standard model is a if we find out some new particle in near future, then of course the SMEFT needs to be incorporated in a larger basis, and that's what our this grid can help you to get this bigger island along with the newly identified particle. And these are some example models of the particles that we have already incorporated at the BSM-EFT. Okay, so now the take-home message is basically, as I started with, the primary aim to pin down the correct nature of the UV theory, and as the plan is going on, so we need a complementary side-by-side impact from the bottom-up and the top-down approaches. And here we are using the observers as a set of effective operators to adjust those BSMs. So once you include more and more observers, you can pin down the correct nature of the BSM theory in a more refined way. And also, if you identify some new particles or new interactions, and then from there you can understand using our this diagrammatic guideline that what kind of UV theory can help you to reach there. And also in the future, if you get new particle, so we are providing also the prescription to extend your SMEFT and such that you can capture that effects as well. So, and I would like to end with this our upcoming thing. So keep an eye for this upcoming thing. So we are trying to improve the theoretical vision, and we have been able to integrate all the heavy scalars employing the modified equation of motion and getting the dimension 8 operators. The reason basically there's proposals that you can use, and the generic perception that if you use the classical equation of motion, we can remove the redundancy, but that is not certainly true, and that eventually, coincidentally actually works up to dimension 6. But if you go beyond dimension 6, classical equation of motion doesn't give you the X and doesn't help you to remove all the redundancy. The George's prescription, which is the field definition, is the nicest one. But what you have noted that if you have to do analysis for so many scenarios, like we did, field definition doesn't have that much algorithmic nature. So we have come up with a new proposal, which we call in the modified equation of motion, and which generates the exact result for the field definitions. And so I will just say that stay tuned for this new result. Yeah, thank you.
Thank you, Professor Chakrabarty, for the very wonderful talk. If anybody has any questions, please go ahead. So I can see one raised hand. Professor Shubhaditya.
Hi, Joydeep. That's a wonderful talk. Yeah, I have a specific question. If I understand correctly, say for example, if I take E plus E minus going to TT bar, now you can consider that you can have a scalar effective operator, right? I mean, and a tensor effective operator. Now the scalar effective operator can be generated by different kinds of new physics models. For example, you can think of type 2 seesaw models or scotogenic models, or for example, there are varieties of 2 Higgs doublet models which will actually give you to the E plus E minus to TT bar scalar effective operator. Now, I mean, if I understood correctly, so is there any way that you are suggesting that
so
just looking at this?
Yes, actually, so are you talking about the operators from SMEFT or below SMEFT, below standard model?
I mean, I'm assuming that the new physics scale is heavy enough so that at E plus E minus to TT bar, suppose I'm looking for.
Yeah, I'm talking about
experimental. Yeah.
Anna, my question is, are you talking about the operators that belong to the SMEFT? Because there's another operator set which is called the low energy effective phase theory left, where you are integrating out the Higgs, gauge bosons, and so on.
Yeah, I'm interested in looking into the low energy incarnation of these new physics models, which gives rise to this effective operator scenario.
Yes.
So, for example, I'm interested in a specific kind of experiments. Like I want to produce TT bar at future E plus E minus experiments. So I have the standard model predictions, and on top of that I have this heavy effective operator contributions to this particular process, like E plus E minus to TT bar.
Okay. So what you can do actually, first identify what is your low energy effective field theory operator. Okay. So now there's so many papers actually we have written also one paper. So this low energy effective field theory operator have a actually mapping in the SNET, and this mapping is not unique. That means basically there are multiple and operators of different dimensions from the SNET can offer you the same left operator. Okay. So you have to identify that, and once you identify that, then from the SNET to EV theory is much more easier.
Yeah, well, my question was specifically that suppose I take different kinds of models which predicts additional Higgses which are present beyond the standard model. And say, for example, you consider type 2 CISA models, or you consider a scotogenic model, which all gives you has to incorporate this additional Higgses basically. Now, what I'm trying to say that in both these cases, if you integrate and if you assume that those heavy Higgses are beyond the scale of ILC to probe at whatever center of mass energy 250 GeV that they are operating on. So they will show up in the E plus E minus to TT bar in terms of this effective scalar operators, say for example. But there are a bunch of new physics which actually contributes to the same same process, I mean to say. So my question was specifically that are you somehow suggesting that there are observables that I can also cook up where just looking into this effective operator procedure of E plus E minus to TT bar, I can distinguish whether this is the type 2 CISA model or some other. So this was basically my question.
So that's what actually you can see. So let's say forget about what is written here. Okay, so you have chosen your observers. Okay, so now these observers are being affected by the which set of operators, and that operators belong to which models they will be degenerate. Okay, so that's why just a particular observer is not sufficient. You cannot break the degeneracy that you can see here. So that right. But once you put all of them side by side, that means if you are passing through all the observers, then you can see the level of degeneracy has been broken so much.
Okay. So, for example, Joydeep, could you remind me what was this ADOPS and BLV?
Okay, so ADOPS are basically the additional operators which do not belong to, I would say, any particular, so they are the new operators being generated, but you cannot dump them in this category. So that's why I call them additional operators until you come up with a new observable which actually being affected by these operators.
I see. Okay, all right. I mean, maybe we will discuss more, but thanks a lot.
Rinku, can you please go ahead and ask?
Thank you. Yeah, so my question was that you are assuming that BSM symmetry is also standard model. Now, if your BSM symmetry is like some higher symmetries, higher base symmetry, I mean, then you can actually filter those observable further. Like there will be some operators which will be protected by higher symmetry, or maybe that will be protected by higher symmetry, but that could generate by RG or some kind of loop level. Is that
So first of all, when you're saying this thing, we're actually ignoring the running of those operators. Okay. And second point, if you have, for example, if you have a left-right symmetry, okay, so then what you have to do actually, you have to perform the breaking of the left-right symmetry first. Okay.
Yes.
And then, because then only your non-standard model gauge bosons, the right wing gauge bosons, and the other scalars and all those things are basically heavy. Okay, and then you integrate them out. So basically, if you have a extended gauge symmetry, you break that, and then you integrate out, because then you come up with the standard, because then you get a subset of the SNET.
Again, my question is, see, there will be some operators which are possible at the level of standard model symmetry, but they may not be possible at the BSM symmetry, and that Wilson coefficient may be like protected and couldn't be generated like in the standard model.
That's why I said that you will get always subset, not all of them.
Yeah, within that subset, I'm saying that there will be some operators that.
So you are saying that, okay, so you are saying basically, if let's say for example, if I have a complex triplet instead of a type 2 seesaw, if I say that complex triplet is coming from vector symmetry model,
yes.
because of its more convoluted structure, yeah, so it will be guided by the what kind of interactions it has. And as you know, this more symmetry is basically more constant, right? So it will have more correlations. Yes, that's true.
Yes. Okay, thank
you. Okay, I can see no more raised hands, so I want to thank you again for this wonderful talk, and we can go ahead to the next speaker. You can unshare. Okay. So our next speaker is Dr. Faiz Abu Azami from ISC Bangalore, and he will talk about BSM Higgs Yukawa couplings. So Dr. Azami, if you can, share this. Yes. Please go ahead.
Thank you for giving me this opportunity. So I'm going to give a brief talk about the Beyond the Standard Model Higgs Yukawa couplings. This is based on work I did with Sudhir Vempati, in addition to previous work with these guys here. So this talk is actually related to the previous one in that it's an effective field theory, except that it's an effective field theory from a different point of view. So first, I will discuss the framework of our EFT, then we'll show how to apply this to the G-2 anomaly, and then try to extend this to the flavor violation in the Higgs sector. So the current measurements of the Higgs couplings to the standard model particles leave ample room for physics beyond the standard model. For example, the Higgs coupling to the top quark is only constrained at an order of 20%, whereas to the muon, it's order 50%. Couplings to higher order operators are either not constrained at all or even less constrained. This motivates us to write a phenomenological bottom-up EFT to search for physics beyond the standard model. For example, in the Yukawa sector, we extend the standard model as such, where here we write the deviation in the standard model Yukawa coupling as delta F1. And we write the other Yukawa-like couplings or higher order Yukawa-like couplings as such. This is reminiscent of SMIFT from the previous talk, except that this is more phenomenological. And here we are not talking about an expansion scale, but we're just talking about deviations compared to the standard model. One can show that there is a one-to-one correspondence between this approach and the standard model effective field theory. If you use a certain level of truncation, for example, you can map this to dimension 6 SMIFT operators, and so on and so forth. However, this is more phenomenologically transparent because in the LHC, you're not measuring any expansion scale. You're really measuring these deviations and Wilson coefficients. So with this in hand, we would like to see some applications into how these can still show us where we can find new physics. So the first application is solving the G-2 anomaly. Now, as you all know, last year, Fermilab confirmed the existence of the muon or deviation of the muon magnetic dipole moment compared to the standard model prediction with a significance of 4.2 sigma. Now, of course, some of you know that there are two lattice groups that dispute this. However, it seems like most results point to the existence of this anomaly. Now, in the standard model, the one-loop Higgs contribution is only 10 to the power minus 14 and is negligible. However, if we allow for deviations compared to the standard model, this contribution is enhanced. So the question is, can the Higgs itself, given a standard model or an EFT framework, can it still account for this discrepancy? So using the previous Lagrangian, we just use the EFT with this, we truncate at the next leading operator. Here, delta mu1, the deviation of the Yukawa coupling in the mu1 sector, and C mu2 is the Yukawa-like deviation. Writing down the relevant diagrams, here we have these 5 diagrams. This first 2 are bar Z type contributions. You can see here you have enhancement in the Z through delta Z1, delta mu1. The second one is a unique. The second, third, and fourth are actually unique because you allow for C mu2. So this is an effective field coupling. And you can calculate this these contributions with an effective Lagrangian previously with a cutoff scale. The first contribution comes from the third diagram right here. The second contribution arises from these 2 diagrams, 4 and 5, as the last diagram, or number 1 and 2, were calculated in the standard model in the literature, so you just rescale them by delta mu. Notice here that in the standard model limit, delta mu and the C's are 0, so the Higgs doesn't contribute beyond. So this essentially parameterizes your deviations versus delta mu, so you can plot this and see whether you can still solve the G-2 anomaly. So here is the parameter space, and we plot C mu2 versus the delta mu2, and we superimpose the LHC bound here in the solid red. As about you can see here, we can still solve delta the magnetic double moment anomaly of the mu1, given the current level of experimental constraints. Of course, here the LHC bound on delta mu1 is plus or minus 0.53 in the Kappa framework. C mu2 is unconstrained, and this is why you essentially can formulate or you can furnish a solution to the G-2. Notice when delta mu1 is 0, you can still account for the solution for the G-2, and this is because C mu is not measured. The reverse is not true. That is, C mu2 on itself is not sufficient to account for this measurement. Here we'll also superimpose the high luminosity LHC run, the projections thereof, and the projections from the muon collider, which essentially is expected to probe the entire range for delta mu1. Now, what are the phenomenological implications of having non-zero deviations? Well, when you have deviations compared to the standard model, you're going to have the standard model Higgs being UV incomplete. The reason for this is that the standard model is the only UV complete theory with the observed particle content, and any deviations compared to the standard model predictions will make it UV incomplete. This UV incompletion will manifest itself as processes with energy growing amplitudes that eventually violate unitarity, as Rohini explained to us in the chat previously. And this will signal the onset of new physics. What this means is that each point in the parameter space here will correspond to a scale of new physics that is unique and can be probed in colliders. So based on the previous talk that we did for the top sector here, we can adapt this to the case of the mu1, and there's only one model independent bound through mu bar to di Higgs. This process essentially gives us a unitarity violating scale through partial wave unitarity given by this expression right here. And as you can see, when you have deviations that are finite, then this would lead to a certain level of Emax. When this deviation vanishes, essentially Emax goes to infinity, which tells you that you retrieve the standard model limit. So the model independent bound can be shown here. This corresponds to the region in the parameter space that can solve the G-2 anomaly, and it ranges between 10 to 12 to 18 TeV, which is beyond what can be probed in either the LHC or the high luminosity LHC. However, we can obtain better bounds if we consider processes that involve the longitudinal modes of W and Z, and if we insist that they conform to the standard model. That is because these processes right here receive contamination from the contributions of the Higgs coupling to W and Z. They're not truly model independent because they will depend on HWW and HZZ. However, if those are assumed to conform to the standard model predictions, then you can obtain these model-independent bound, and the bound on the scale of no physics can be lowered to between 4 and 5 TeV, which is within the reach of the high luminosity run of the LHC. Another interesting fact that can result as a non-zero delta mu1 or C mu2 is the enhancement of the Higgs reduction. Now, in PP colliders, then this enhancement will come through gluon fusion with the mu1 running through the loop as such. However, explicit calculation will show that these are negligible because of the smallness of the Yukawa coupling. However, if one considers the proposed mu1 collider, then through mu bar to Higgs production, one can have a significant production through the contact term, because now C mu2 is allowed to be non-vanishing. And it's easy to show that the tree-level cross-section is actually significant. Here we plot the cross-section that and we superimpose the region in the parameter space that corresponds to G-2. And we can show that there's actually significant cross-section that ranges between 7 and 23 picobarn, which is quite significant and gives further motivation for building the high luminosity or the muon collider. So furthermore, this represents the first work that I did with it here a month ago. And now we can also use the same kind of phenomenological Lagrangian in order to generalize to effective Lagrangians, including flavor violation. We can essentially do this by writing this Lagrangian and promoting Yij and Cij to become matrices that might be non-diagonal. Here, these will parameterize the flavor violation. Previously, flavor violation through non-diagonal Yij has been studied extensively. However, for the first time, we allow for non-minimal violation in the Yukawa coupling Cij. So in our investigation, we set Yij to be standard model, and we focus on flavor violation from Cij like this. Now, this is work in progress. Currently, we finished doing the muon, constraining the muon or the lepton sector. For example, here we can have a constraint from the decay of a lepton to lepton plus gamma, such as tau to mu gamma, tau to e gamma, or mu to e gamma. This proceeds through the two-loop diagram like this, with either tau, mu, or e running in the loop. The one-loop diagram is vanishing, and we can furnish here the following constraints that come. Each set comes from a different particle running from the loop. As you can see here, we can essentially furnish some stringent constraints, and for the first time, to the best of our knowledge, these constraints were calculated in the literature. We can also constrain these through the decay of leptons to 3 other leptons. For example, tau to 3 mu, tau to 3e, or mu to 3e, in addition to mixed decays. Those proceed through one loop like this, and we can furnish these constraints on these couplings as well. Other constraints do exist, but they are not as strong as these. And what remains is to extend this treatment to the quark sector, which is still being done. So I'll be brief. Let me conclude here by saying that the key takeaway here is that the Higgs sector remains a prime location for searching for physics beyond the standard model. This is because the current constraint on the Higgs couplings to the rest of the standard model, particularly the Yukawa and Yukawa-like couplings, leaves ample room for physics beyond the standard model. Now, it's important to look into the coupling or the effective coupling C mu2, because it can still accommodate for a solution to the G-2. This solution will correspond to a conservative scale of new physics that ranges between 10 to 18 TeV, which can be lowered to 5 TeV if the Higgs coupling to the massive gauge bosons is standard model-like. Flavor violation could arise minimally through Cij, and we advocate this to be investigated. The key takeaway of this study is that the couplings C mu I or C mu2 needs more interest in the literature. To the best of our knowledge, no current or future experiments propose measuring CMU2. They do so for the top quark, CTOP2, which is currently constrained at about plus or minus 20%. However, we think that we need more similar interest on CMU2 as well. So with this, let me conclude my talk and keep it brief and see if you have any questions.
Thank you, Dr. Azhar, for the very nice talk. Yeah, if anybody has any question, then please go ahead. I don't see any raised hand. So let me ask one question. So why do we get better bounds in muon colliders?
The reason for this, if you have a muon collider, let me get back to here. For PP colliders, what you will have is that the Dihiggs enhancement will come through these diagrams with the muon going through the loop. Now, of course, this is dominated by the top quark, and the muon collider or muon coupling is small, so you get a negligible contribution. However, if you have a muon collider, indeed, you will have this process mu bar to h bar proceeding through a contact term, and because CMU2 is unconstrained, essentially it can have a sizable value as compared to the deviations in the Yukawa couplings. You can have a large enhancement of the Dihiggs.
Okay. Thank you.
You're welcome.
So if nobody has any question, then let's thank Dr. Ajame again for the very wonderful talk. And let's go ahead to the next speaker. Yes, so our next speaker is Rituja Sengupta from ISC Bangalore, and she will talk about light neutralino dark matter in MSSM contributing to Higgs invisible decay. So Rituja, please go ahead.
Hello, can you see my screen and hear me?
Yes, perfect.
Okay. So hello everyone, I'm Rituja Sengupta, and I'm very grateful to have this opportunity to present our work in front of you. I'll be talking about light neutralino dark matter in MSSM contributing to the Higgs invisible decay, which is based on this recent work done in collaboration with Dr. Rahul Kumar Burman, Professor Genevieve Belanger, Professor Biplab Bhattacharjee, and Professor Rohini Godbole. So we all know that the standard model of particle physics, which is very successful in explaining many fundamental phenomena of particles, is very well tested at the quantum level by the precision measurements. And with the discovery of the Higgs boson at the Large Hadron Collider in 2012, the last piece of the standard model was found. However, there are still many unanswered questions like the origin of neutrino masses, dark matter, matter-antimatter asymmetry, and no conclusive hint of new physics as of yet. So we ask the question, can Higgs boson be the messenger of new physics? So what do we mean by this is that the Higgs is acting as a connection of new physics particles to the standard model. So new physics particles have coupling to the standard model Higgs boson, and through that they couple to our standard model particles. And this is motivated both theoretically as well as experimentally. Now, these new particles can be dark matter, and there will be a talk by Professor Shubhaditya Bhattacharya talking about how to probe dark matter through the Higgs portal. But in this talk, what we are talking about is how can we get the invisible decay of the Higgs boson? Now, if our dark matter particle is lighter than half the Higgs boson mass, then this dark matter can be produced from the on-shell decay of the standard model Higgs boson. And this is basically the invisible decay of the Higgs boson. So one possible dark matter candidate is the lightest neutralino in the minimal supersymmetric standard model MSSM. And so before proceeding further, let us understand what we mean by lightest neutralino in the MSSM. Just some basic stuff. So from extending standard model to MSSM, we have 2 Higgs doublets in the MSSM Higgs sector, and that gives us 5 Higgs bosons instead of the 1 Higgs boson in the standard model. Here, the lightest CP even Higgs, which is denoted by this small h, is our standard, the observed Higgs boson. And in the supersymmetry, so for every corresponding Weil fermion, we have a superpartner, which is a complex scalar, and vice versa. And for each gauge boson, we also have a Weil fermion. So if we look at the standard model particles that we have, so for every fermions, we will have a scalar fermion as the superpartner. For Higgs bosons, we'll have Higgsinos, and for gauge bosons, we'll have gauginos. Now, with this information, let us look at the electroweak sector, and we look at the superpartners of the electroweak gauge bosons and the Higgs bosons. So we have the BINO, the VINO, and the 2 Higgsinos. So they have 4 neutral gauginos, and 2 neutral gauginos and 2 neutral Higgsinos, and 2 charged and 4 charged inos. So they mix together to give you 4 neutralinos and 4 charginos, and these are mass ordered. So the lightest neutralino is the neutralino coming from the mixing of these 4 inos, and this has the lowest mass. So now, if SUSY had been exact, then the superpartners would have the same mass at this as their standard model counterparts. But we know that SUSY is broken, and therefore all the superpartner masses are parameters of the MSSM. And if we have R parity conserving SUSY, then the lightest supersymmetric particle, which we call the LSP, will be stable. So if this LSP is neutral, then it can be a dark matter candidate. So this talk, we are focusing on lightest neutralino, which we discussed what we mean by lightest neutralino a couple of slides before, is our LSP. And since it's neutral, it is also a viable dark matter candidate. And since we are interested to look at the Higgs invisible decay, its mass is less than half the Higgs boson mass, that is around 62.5 GeV. Now, this scenario has been previously studied in many works, but this has particularly become interesting now because we have new data at our disposal, and run 3 is also coming up. So a fresh look at this scenario is much needed to understand whether what's the current status. So this is the MSSM parameter space where so these are all the parameters that we scan over, where M1 is the BINO mass, M2 is the VINO mass, mu is the Higgsino mass parameter, and it can have both the positive and negative signs, and we have studied them separately. Tan beta is the ratio of the webs, MA the pseudoscalar mass, and these here, this side parameter, they the trilinear plane and MP mass. So we scan over these, and as discussed earlier, that our light neutralino to be below 62.5 GeV, it has to be dominantly BINO due to limit on chargino mass. Now, the coupling of this LSP to the Z and Higgs bosons depend on the BINO, VINO, and Higgsino components in it. So here, these are the two equations. The 2 equations here show the coupling of this chi1 0 to your Z boson and the Higgs boson, and you can see that these depend on this N13, N14, N12, and N11, which are basically the mixing matrix components. So the next question is, what will be our next to lightest supersymmetric particle, which we call the NLSP? And in this study, we have mostly considered Higgsino due to the already existing strong limits on VINO and NLSP. So now, we have used fine Higgs as our particle spectrum generator. And moving on, so we can see this is a large parameter space, and now we already have some existing constraints which will play a role in constraining our parameter space and giving us results. So the first one is, of course, the LEP constraints, which include the invisible decay of Z boson from new physics, then the charge-ino mass limit, which your charge-ino has to be greater than 103 GeV, and then some cross-section of associated production of neutralinos in final states with jets. The second set of constraints that we apply on our parameter space are the flavor observables, are constraints on the flavor observables. So these are rare processes in the standard model, like this FCNC flavor changing neutral current process, like B2S gamma, which proceeds through loop in standard model, and it will receive contribution from the MSSM, and therefore precise measurement of the branching of these processes constrain the MSSM parameter space. And we have here applied these constraints. And then the next and a very important set of constraints come from the Higgs constraints. So we have already discussed that out of the 5 Higgs bosons, which we get from the MSSM, in the MSSM, the lightest CP even state, we think that that is our observed Higgs boson, and therefore its mass should be around 125 GeV, but there are theoretical uncertainties. So being conservative, if our MSSM parameters can give us a Higgs mass between 122 to 128 GeV, we take that point. Then the second set is the Higgs signal strength. So already LHC has observed Higgs in a number of production modes, as well as it has measured different branching modes of the Higgs, and comparing them with your theoretical expectations, you can calculate these Higgs signal strengths and see whether your MSSM parameters do not change this signal strength observables very much. Then there are heavy Higgs searches. So our MSSM's Higgs sector has heavy Higgses, and you can look for their decay in the Large Hadron Collider and search for them, and then place limits from the non-observation of any events. And this here actually excludes a large chunk of the parameter space. Here in this plot, the x-axis is the pseudoscalar mass Ma, and the y-axis is the tan beta. And you can see that this large region, low tan beta, high tan beta for low Ma is ruled out by this Atlas analysis. And then we have the invisible decay of the Higgs boson. So our Higgs boson can decay to Chi 0, and the branching of such process has to be less than 14.5%, which comes from this recent Atlas analysis using the VBF topology. Now our Chi 0 is a dark matter candidate as well, so it has to satisfy dark matter constraints. The first one being the relic density. So the present observed relic density of dark matter from the Planck collaboration is around 0.12 with an error bar of 0.001, and within 2 sigma we demand that our LSP's relic density should be less than 0.122, and if it's underabundant, then dark matter can be multi-component. Then there are direct detection constraints, which constrain the dark matter and nucleon cross-section. In this plot, that y-axis is the WIMP nucleon cross-section, and the x-axis is the dark matter mass. There are many experiments constraining this, and we have used both spin-independent limits and spin-dependent limits. And you have to scale this direct detection cross-section with this factor Xi, which is basically the factor of relic density that it is satisfying. So if it's underabundant, then limits will become weaker, and then you have to scale your sigma direct detection accordingly. So now the last set of constraints is the electroweak-ino constraints. So these are results of direct searches of charge-ino and neutralino at the Atlas and CMS experiments of the LHC. So we are talking about processes where we produce this charge-ino neutralino pairs, and they will decay to W boson and neutralino 1, or Z and Higgs boson and neutralino 1. And neutralino 1 being the dark matter candidate, it will leave a missing transverse energy signature in our collider. Along with that, the modes of these vector bosons and the Higgs, since they are cleaner, they have been used in the past, and there are, conventional analysis of 3 lepton plus missingity, which are being done to constrain these charges.
You have 5 minutes long.
Okay, sure. But since these have low branching, therefore they are sensitive to lighter NLSPs. But recently, both ATLAS and CMS experiments have actually analyzed the hadronic final states, and these increase sensitivity to heavier NLSPs. So if you look at this plot, this x-axis is this chargino or second neutralino mass, I mean your NLSP mass, and the y-axis is your dark matter, I mean this LSP mass. And you can see that this can exclude up to 900 GeV of NLSP, whereas from leptonic final states, you can only go up to 400 GeV. So we have implemented these electroweak constraints using SMODELs. Now the results for positive mu scenario, this is what we have found, and the x-axis is the dark matter mass, the LSP mass. Y-axis is the direct detection cross-section scaled with its relic density. And here all the gray points are satisfy all the constraints from LEP, flavor, Higgs constraints, relic density, and direct detection experiments like Xenon 110, Pico 60, and Panda X40. And the colored points, they satisfy all the electroweak constraints from the LHC. And here we can make three observations. The first one is that relic density and direct detection allows points only in the Z and Higgs funnel regions, where the mass of the chi-1 zero lies within some half of Z boson mass and half of Higgs boson mass. Second one is after applying this electroweak constraints, the colored points, I mean the Z funnel is completely ruled out, but in the Higgs funnel, you either have very light Higgsinos around 150 GeV or very heavy Higgsinos above 855 GeV. But if you apply this LZ limit, which is very recently given by this LZ collaboration with 60 days of data, this completely rules out the positive mu scenario. So what happens in the negative mu scenario? So here, the first plot is similar to what we have seen for the positive mu, only that here the y-axis shows a spin-dependent direct detection cross sections, and here we see that we have points in both the Z and Higgs funnel regions which satisfy all the constraints. But once we apply the LZ limit, again in the spin-independent direct detection, the heavier masses in the Higgs funnel region gets ruled out, and only a very narrow, marginally allowed region is left, which is light. And these are very marginally allowed, so these are expected to be probed in the near future by the LZ experiment with its full 1000-day exposure. And this is again the result for mu less than 0. The negative mu scenario, but in a different, the y-axis here shows the NLSP mass, so the neutralino 2 mass, and here these stars are all the points which satisfy all the constraints, and we see that they are mostly very light Higgsinos. So this inset plot shows how, how far are they from getting probed in our colliders. So this is the SMODEL's R value, and a smaller R value indicates that the point lies way outside the current limit or current analysis, and a R value close to 1 indicates that it just lies on the border. And we see from this inset point that some of our points have very small values of R. And these are basically evading ATLAS searches for charginos and neutralinos in the leptonic final states, since these are very light Higgsinos. So leptonic final states are more effective in probing that. And for that, we performed an analysis with the leptonic final states using XGBoost. And our results show that these points, this narrow region that is evading all the current constraints, could be probed with upcoming analysis of the run-2 data, which have not yet been implemented in SMODEL. So just to reiterate that we are using the SMODELs framework, so any analysis that is not included in SMODELs won't the results are not here. So SMODELs actually this is the latest version, so it includes all the published results. But yes, we should keep an eye for any new results. Or if run-2 is not able, run-3 will definitely be able to look into this narrow region, provided the systematic uncertainties can be brought under control, because we have seen that systematic uncertainties in this narrow region plays a crucial role. So just my concluding remarks that the recent results from the electroweak searches at the LHC and the LZ dark matter direct detection experiments have severely constrained the positive mu scenario. and it has squeezed the parameter space to light Higgs in the negative mu scenario for a light neutralino thermal dark matter in the MSSM, which is lighter than half the Higgs boson mass. And the run 3 of LHC can target this low mass Higgs, and dedicated analysis might close this narrow gap. So this is also a menu for the run 3, that they can devise their analysis in such a way that this whatever region is left out, that can also be probed. So at present, we are at a very exciting juncture where the experiments lined up might just include the possibility of a light neutralino thermal dark matter in the MSSM altogether, or we might be very close to start observing the first hints of new physics. That's all. Thank you for your attention.
Thank you, Rituja, for a very interesting talk. If anybody has any question, please go ahead. Yes, Professor Sudhir.
Hi, Rituja. How low can be this light Higgs be? Meaning, what is the lower limit?
Yeah, so the lower limit, we have found points from around 145 to 149 to 155 GeV. So this is basically the very narrow region where it becomes, the decay is off-shell. So the off-shell analysis, so this W.
When you say Higgsino here, you mean pure Higgsino?
This Z.
Hello?
Her internet is slightly unstable. Can you please repeat?
Sensitivity. Yes.
Right. When you say Higgsino,
these are in the Higgs funnel, and in the Z funnel around 130 to 140 GeV.
Okay. All right. When you say here Higgsino, is it pure Higgsino? How much is the Higgsino component?
Yeah, it's mostly, so here our BINO is at, so our we have started our BINO scan from around 1 TeV. So, and our Higgsinos are around 130 GeV. So they are more, dominantly Higgsino, but they will have some admixture, slight admixture, but yeah, they are mostly Higgsino-like, almost pure Higgsinos, because the BINO is at below 60 GeV. So the BINO is, the Chi10 is more dominantly BINO, and it has a slight Higgsino admixture, and then the NLSP is your Higgsino, and your VINO is sitting above 1 TeV. So these are
okay. 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 Thank you. Yeah.
Can I just add one comment?
Yeah, LSP is completely BINO.
Can I just add one comment?
LSP is completely BINO, or?
Yeah.
Rituja's internet is not working, I guess. What was your question?
What was your question, Sudhir?
So Rituja is here. I am giving her my microphone. You can talk to her.
Yeah, hello. Hello, can you hear me?
Yes, we can hear you.
Yeah.
Yes, I can hear you. Yes.
Yeah. So, what is the question?
I don't know why Sudhir may not be able to speak, but what he was asking Ritaja was about the Higgsino BINO content of the LSP and NLSP.
Yeah.
And that was at least I understood that question about that. It was about
yes. So LSP is dominantly BINO, so around 99%. Greater than 95%. It's almost it has the BINO component, and the rest is Higgsino.
Sorry, one comment, Ridhaya. Have you
Yes.
checked the recent result from the Higgsino searches? Because this the limit, as far as I remember, for the simplified models are at least greater than 300 or 400 GB. Like, did
Yes,
you
so we are, yeah.
change the limit?
So we are using the latest version of models, which includes all the latest results. I mean, all the 139 femtobarn inverse results of Atlas and CMS. And these points, I mean, so we are having, I mean, so in the simplified scenario, your limit excludes till 400 GB or so for Higgs-Zenos. But in the very light region, I mean, this branching, I mean, so that is the simplified case. And here for each particle spectrum, Swaddles is calculating the branching ratios and then checking with the efficiency maps. So here we are getting this very low, very narrow region at the light Higgs-Zenos, which are, but there, as you can see, I mean, not able to show my slides, but these are evading some Atlas result, which was about 20.3 femtobarn inverse. So that was some dedicated optical analysis, but we don't know whether if you update that analysis, what will be the result here? But we have that 139 femtobarn inverse leptonic analysis in this list.
So in the Z and the H funnel regions, these are still allowed, basically. This range of Higgs-Zenos you consider for your model.
Yes. For our model, in the positive view, it's mostly getting rolled out due to the recent LZ limit. But in the negative view, we are still having these narrow, these points in the very narrow region at light Higgs-Zenos, around 150 G.
Okay. I think you can point, you said that in your talk, Ritaja, but maybe you can emphasize it once again, that those particular points that are allowed are due to the mass relations between the different NLSP and LSP, which allows this points to evade the searches.
Yes.
So perhaps you can emphasize. You said it very clearly.
Yes. So these are, the mass difference, the mass of the Higgs-Zeno, the NLSP and LSP such that your your Z and Higgs bosons are produced optical and you are looking at the optical limits. So that is, it needs some dedicated analysis, and the branching ratios will also suffer, due to such symptoms. So that's why these are getting.
Professor Ghosh, if you have a question, please go ahead.
So hi, this is a nice talk. So just a naive doubt. So your lepton masses were around 2 TeV. So what about the G-2 constraint?
Yeah, so we tried looking at that, but the thing is, in our positive view scenario here is, even if we keep the leptons decoupled, it's getting ruled out from this LZ limit. The positive view is the one which actually will favor the muon G-2 anomaly. And before the LZ limit, we were actually getting points which could satisfy the muon G-2, where we were bringing the leptons down, and we were trying different kinds of things where we keep the leptons light, and also we bring the muon below, above. I think the current limit is around 700 GeV, so we were keeping it just above 700 GeV, and we were also trying some things. How we can keep it below 700 GeV with different possible spectrum, such that it doesn't get ruled out by the current electromolecular limits. But the point is that the positive mu in this funnel regions, in the Higgs and Z funnels, is getting ruled out due to the LZ.
Okay, so another quick question. So could you please comment on this, the fine tuning, because some of your squat masses was also around 5 TeV.
Yes.
So the issue of the fine tuning in.
Sorry, sorry, can you repeat the question?
Yeah. So some of the squat masses, for the first generation, it was around 5 TeV, if I remember correctly.
Yes.
So what about the fine tuning issues, the parameter tuning, and how sensitive your results to that parameter tuning?
So we have, I mean, we have not checked the fine-tuning measure. I mean, we have we are only playing with the third generation quark masses to ensure that we get the correct Higgs boson mass, and we have decoupled the first two generations from the spectrum.
May I respond also to Pradipta's question?
Sure.
See, Pradipta, I think fine-tuning is no less or no more than any other SUSY scenario, but our results are completely insensitive to the quark masses that we are choosing.
Okay.
None of the experimental signatures we are looking at, or none of the indirect constraints, push our quark masses beyond the usual fine-tuning limits that are sort of independent. This analysis is independent of that question.
Okay.
That's really what I want to emphasize.
Okay. Yeah, that was
It's no more or no less than anybody else who is believing in PMSSM.
Yeah. The 19 parameter business. Okay. Thank you.
Thank you.
Thank you, Rituja, for the interesting talk. I don't think we have any more questions. So we can close this session and we will reconvene at 2:15. Thank you, everybody.